Thanks for joining. My name is Ruslan Bartsey. I'm head of data science program at the Ukrainian Catholic University. And today we have a master thesis defense and our master students will be defending their thesis. And so for short context, our program exists for 9 years, and in this 9 years, we have 104 graduates of our program so far. Yes, hopefully this year we will have 18 more. So our defense will be 2 days. The first day we will have 9 students, and the next day we also will have 9 students. And I would like to introduce our examination committee. So in our today's examination committee, one moment, I will be Rostislav Hrenev, Doctor of Physical and Mathematical Science, Professor, Head of Department of Applied Mathematics. Also, Alexey Molchanovsky, Senior Lecturer at the Department of Applied Mathematics and Statistics of the Faculty of Applied Sciences, founder of this program, and today he is Chief Innovation Officer at our university. Vadim Yermolayev, candidate of Physical and Mathematical Sciences, Professor at the Department of Computer Science and Information Technology. We also have 2 guests today. Serhiy Stirenko, a chairman of today's committee. He's Doctor of Technical Sciences, Professor, Vice Rector for Research at Igor Sikorsky Kyiv Polytechnic Institute, and also Natalia Sakhnenko, today's industry expert, Associate Professor, Doctor of Physical and Mathematical Sciences, also at Igor Sikorsky Kyiv Polytechnic Institute, and me, Ruslan Bartsey. For me, as for the director of this program, master defense is always a bittersweet moment because we've been working together for almost 2 years with the students. So this is the bitter part, and the sweet part is that finally we reached this moment, and my students are 1 step away from their master's qualification. And as you may see, even the weather today likes that we have master defenses, we have a blue sky and sun is shining. So about today's program, we will have 2 presentations, then 20 minutes break, then we will have again 2 presentations and 1 hour break for the lunch, then 3 presentations, 40 minutes break, and finally we'll have yet another 2 presentations. So the rules are the following. We will have up to 25 minutes for the presentation and up to 15 minutes for questions and answers. And examination committee will have a priority in questions, and if there will be questions from the audience would have a chance to ask the question also. And in the end, we will announce the results for all the students. So good luck to everyone, and we will start from first presentation by Yury Шинкарьов, who was advised by Veronika Solopova, and the work is entitled Developing a Robust Text-Based Sentiment Analysis Model for Ukrainian Social Media. Yury, please.
Okay, can you listen to me? Okay. Good morning to everyone. My name is Yury Шинкарьов, and I'm happy to open the event today and to present my master's thesis. But before this, I would like to acknowledge my scientific advisor, Veronika Solopova from Technische Universität in Berlin. and express my gratitude to her for the valuable guidance provided throughout this research journey. Our research addresses an important gap in Ukrainian NLP resources, and the work we are presenting is about finding a path towards a robust sentiment analysis model for texts in Ukrainian social media. And the presentation is structured as follows. We will start with some theoretical parts, outlining research gap and some highlights from the literature, and then we move on with the presentation of a new created dataset named Cosmos, as well as our methodology and results. And the final part is about conclusions and future directions of work. And I start with the question about how we define the sentiment analysis. This is important because sentiment analysis is quite old term and a broad one, and we need to be sure that everyone here is on the same page. So sentiment analysis can be defined as the process of computationally categorizing opinions expressed, in our case, in some piece of text. And when we say opinion here, we mention polarity, because there is a lot of research focusing on other characteristics, for example, emotions or some authors' intentions. Here we talk about polarity. And we can measure the polarity on different levels of some text, entity level or considering sentence. In our research, we talk about detection sentiment on the level of a text as a whole. So we call it document. For example, social media posts or some comment from an internet forum can be such document. And the next question is the question of why. Why detecting sentiment is important. Sentiment analysis serves as a crucial tool for businesses and researchers for understanding public opinion at scale. For example, businesses can use it to monitor their brand reputation and then optimize marketing strategies respectively, as well as researchers can use it to study some societal trends, political discourse, and other aspects of human behavior. And the field has been growing in popularity in almost every year since 2017, then the transformer architecture was firstly introduced. And it may seem that the area is quite saturated already with research. And in some respect, this is true indeed. However, we will see that the work is far from complete. And even after this presentation, there will be still promising directions of further research, especially when we talk about low and mid-resourced languages like Ukrainian. And when we talk about monitoring opinion at scale, we need a reliable and good, big enough source of data. And social media platforms provide an incredibly rich source of real-time, first of all, and user-generated data, making them available for our task. And on this slide, we can see the answer to the question why we stick to the Telegram posts as the main data source for our solution. Firstly, the Telegram is the most popular social network in Ukraine, and it demonstrates a growing popularity year by year from 2022 to 2024. And for now, around 78% of people in Ukraine uses it as the main platform to consume content, to read news and communicate. And the second reason is that the Telegram has an open API and has no restrictions for researchers to scrub the data, collect the data, and then publish the results. And we move to the research gap. There exists a significant imbalance in NLP resources available for different languages. While sentiment analysis for English, for example, has achieved remarkable accuracy rates, there are examples of papers on the slide presented exceeding 90% of accuracy in many cases on public benchmarks. Meanwhile, many other languages remain underrepresented in this technological advancement. And the Ukrainian NLP community currently lacks a high-performance and, importantly, open-source sentiment analysis model comparable to solutions available for, not even for English, but for other European languages like Lithuanian, Hungarian, and Polish, for example. And our research addresses this gap by proposing a comprehensive approach to developing a high-quality model specifically designed for Ukrainian social media. And the main hypothesis driving us is that by combining advanced transform architectures with appropriate pre-processing techniques and comprehensive Ukrainian-specific training data, we can develop the needed model. We moved to the literature part, and to ensure a comprehensive review of existing research, we conduct an iterative process of examination of citation networks, starting with this carefully selected sets of seed papers. We identified 9 key papers ranged from fundamental ones with thousands of citations to more specialized, focused on Ukrainian sentiment analysis. And there are 3 key observations here. Firstly, we keep our attention on works describing solutions for the Ukrainian language, and we identified 7 relevant papers connected to the topic, including ones from the seed set. And find out that there is no publicly available code or data that can be used as a benchmark for us, so we cannot make a comparison in our research, the starting point. However, there are good examples of commercial solutions available on the market, showing that our research goals are feasible. The second key observation is that the most significant breakthrough in the field came with the introduction of transformer architectures. Fine-tuned BERT models achieved state-of-the-art results across various sentiment analysis tasks. These models served as the main solution or as a baseline in the most surveyed studies. And additionally, it is important for us, transformer-based architectures can handle cross-lingual sentiment analysis, which is making them valuable for our use case. And last but not the least, more recently, conversational LLMs is fighting for the fields. Models like GPT, Gemini, Llama have introduced new possibilities for sentiment analysis. Their key advantages are deeper understanding of context because of the size of the model, respective models. And they demonstrate, and the second advantage is that they demonstrate remarkable success in zero-shot and few-shot learning scenarios. The last one is a quite big advantage. However, these models face limitations and challenges in large-scale applications and can introduce biases to sentiment solutions. And on the next slide, we can see the results that tell us that the specialized models have not been dead yet. The picture showing the class distribution of GPT 3.5 model versus human validation. The labels were made during the annotation project made by Ustanovich and Barbosa. They annotated social media texts about the war in Ukraine. And it highlights a weak point. We can clearly see the bias towards more negative emotions demonstrated by GPT 3.5 in comparison with human labels. And this can be a problem. Okay, let's move to the data part. And a critical component of our research involves analyzing existing data sets and determining whether determining their suitability for our task. And we collected 5 data sets that could potentially support our research, spanning the years 2022-2024. Most of these data sets aren't publicly available and were kindly shared by other NLP researchers from the Ukrainian community. And our analysis leads to a clear conclusion that none of the investigated data sets are fully applicable to our problem. The limitations are on the slide. There are whether inappropriate language distribution, like in the last data set, or insufficient size, or inapplicable sentiment orientation. For example, as in the first two data sets, where sentiment defined as news orientation towards Ukraine, but not as polarity as in our case. Okay. And this justifies our decision to create a new data set to the field that properly represent the current linguistic landscape of Ukrainian social media. We named it Cosmos, or Code-Switched Multilingual Sentiment for Ukrainian Social Media. The dataset includes news, posts, and comments, mainly from scrapped from Telegram platform, as well as a minor portion of reviews from open platforms like Hotline.ua and reviews of Yakabu books. We did this in order to dilute the topics, the distribution of topics in our dataset. And the total volume of collected text was around 13,000. However, we removed spam messages, boilerplate content during preprocessing. So the resulted dataset size is about 12,000. And to annotate the data, we use 4 sentiment classes presented on the slide. There are positive, negative, neutral, and mixed sentiment. They are quite distributed across existing research. And this classification schema allows us effectively cover all possible emotional states without introducing excessive granularity. And also, we get special attention to the language distribution in our dataset. For now, Ukrainians consume from around from 20 to 30% of content in languages different from Ukrainian, according to the latest sociology research. And the main second language is Russian, so we keep a respective portion of it in the data. And also it is important to identify and work with code-switched content, which is also quite distributed across informal domains, such as social media texts. And for annotation quality assurance, we're implementing several best practices from the literature. To ensure consistency across different annotators, we're employing inter-annotator agreement metrics, Koch and Kappa in our case, and designing structured questionnaires that clearly define each sentiment category. As a tool for annotators, we developed a Telegram bot providing a detailed guideline and with examples of each sentiment class. And the key approach in the guideline is to classify text by identifying key words or phrases in the text and not relying on own interpretations and feelings of an annotator. In the result, we achieved quite substantial Cohen's kappa equals 0.79, means substantial reliability of annotations. And also we see some bias in the resulted distribution of labels towards neutral and negative classes. So augmentation techniques will be used to prepare the data for the training step. And based on our literature and review and gap analysis, we tested approaches that, in our work, we tested approaches that work as the state-of-the-art solutions for other European languages, as well as for English. And our models can be divided into 2 logical groups. First, we established a baseline using general purpose conversational LLMs, GPT-4o and DeepSeek, and an open source alternative DeepSeek v2 chat. Second, we fine-tuned the models from the BERT family. Specifically, we worked with Uka Roberta, a model which was additionally pre-trained for Ukrainian texts, and Modern BERT, a multilingual model optimized for various languages. And these models have demonstrated strong performance in other research on low resource tasks when fine-tuned properly. For evaluation, we will use we used the classical metrics while accounting for class imbalance presented in the dataset. This includes F1 score, which is the most popular option across existing literature, as well as other confusion matrix metrics as precision and recall. And we will also assess the reliability of our solution, of our models, using expected calibration error. The key idea here is to evaluate how well the model's actual confidence coincide with the probability, actual likelihood of an outcome. In other words, how calibrated the model is. And let's start to review the results. Let's look at the results of our prompting solutions, GPT-4o and DeepSeek VChat. The table shows the macro F1 scores across differing prompting strategies we used, with the best performance highlighted in red. And we can see several important patterns here. First, across all configurations, English prompts consistently outperform Ukrainian ones for both models. And this language gap was particularly pronounced in zero-shot environment, in zero-shot setting, where we see larger differences between the Ukrainian and English prompts compared to few-shot scenarios. And the second is that GPT-4o demonstrated superior performance across all settings, prompting strategies, with its best using few-shot English prompting. This consisting advantage of GPTs likely reflects its stronger multilingual capabilities, which is particularly relevant for our use case. And we can move on to our data augmentation experiments. We tested two strategies across all four models. We compared the original unaugmented data results with back translation, the first strategy, and word substitution. The first strategy involved translating text to an intermediate one, which is English in our case, and then back translated to the original language, creating paraphrases. We utilized LibreTranslate, an open source machine learning translation tool, to perform the translation process. The second strategy involved replacing individual words or phrases in the text in the dataset with synonyms or contextually appropriate alternatives while preserving original sentiment. We do this by access the GPT-4o via API with a temperature parameter of 0.7, which was selected to produce contextually appropriate replacements. The model was directed to preserve the original sentence structure and linguistic style. After this, we also do manual checks with back translation and as with word substitution that we selected a sample of texts from the augmented results and review that sentiment is preserved. And the result reveals some interesting insights about how different models respond to various augmentation techniques. It's quite logical that GPT-4o and DeepSeek yielded the best results on the original data without data augmentation, because with the scores of 0.56 and 0.52, because we did not fine-tune the model, so they only accumulate the error as the dataset size increases. And the picture is different for smaller models, specialized when we use fine-tuning. Especially mBERT showed its best performance with word substitution strategy, achieving a macro F1 score of 0.58, which actually outperformed both of conversational LLMs. And Roberta, with also word substitution strategy, emerged as our strongest classifier, achieving overall a macro F1 score of 0.64 on the test set. This represents a significant improvement over its performance with original data and back translation. These findings also highlight the critical importance of selecting appropriate augmentation strategies based on the model architecture and available resources. And let's now examine how our two best models, UCR-Roberta and MBERT, handle different languages, language categories within Cosmos dataset. The table shows precision, recall, and F1 scores across 4 language categories: pure Ukrainian texts, pure Russian, code-switched examples, and the overall averaged metrics. UCR-Roberta demonstrates remarkably consistent performance across all languages, all language categories. It achieves its best macro F1 score of 0.68 on code-switched content, with Ukrainian content following closely with results of 0.63, and Russian content 0.59 of F1 score. And MBERT shows a different pattern altogether, while it achieves higher precision in almost most categories, particularly notable for Russian language precision, 0.81. It struggles significantly with recall, especially for Ukrainian texts, where recall drops just to 0.44. And these results highlight UCR-Roberta's superior ability to handle the multilingual nature of Ukrainian social media, maintaining robust performance across all presented languages, which is a crucial advantage for the chosen domain. And let's move on to the calibration quality of the best models by looking at the expected calibration error measurements. Model calibration tells us how well the predicted confidence scores align with actual accuracy, essentially whether a model says it's 80% confident and it's actually correct 80% of times. These reliability diagrams show the relationship between the predicted confidence and empirical accuracy across different language usage subsets. The diagonal line, dashed line, represents perfect calibration, where predicted confidence perfectly aligns with actual accuracy. Looking at the overall calibration in panel A, UCR-Roberta demonstrates significantly better calibration with an error of 0.17 compared to MBERT's twice as large 0.32. UCR-Roberta's bars are much closer to the dashed line, indicating more reliable confidence estimates. On Ukrainian-only texts, this is panel B, models show quite different calibration. Models, MBERT and UCR-Roberta, show quite different calibration, with UCR-Roberta again performing better. On the other hand, for Russian-only texts, we see similar calibration results. This demonstrates that UCR-Roberta did not lose their knowledge of the Russian language during specific pre-training for Ukrainian texts, and that this knowledge is preserved by MBERT. Perhaps most importantly, for practical applications on code-switch texts, which are common in social media, UCR-Roberta again shows superior calibration compared to MBERT. This results indicates that UCR-Roberta not only performs better in terms of performance metrics, accuracy, recall, F1 score, but also provides more trustworthy results. And we can move to the conclusions. Through this work, we aim to contribute both practical and methodological insights to the growing field of Ukrainian NLP. And as a result, we developed a Cosmos dataset, publicly available corpus of around 12,000 of text covering Ukrainian, Russian, and code-switched content, annotated into 4 sentiment categories. The dataset achieved substantial inter-annotator agreement and fills a critical resource gap in the community. Second, we evaluated 2 augmentation techniques, strategies, back translation and word substitution, by using LLMs. And our experiments demonstrated that targeted word substitution could substantially improve fine-tuning results while back translating often degraded model performance. Third, we fine-tuned two compact transformer-based models, MBERT and UCO-RoBERTA, on the Cosmos dataset, and fine-tuned UCO-RoBERTA combined with the word substitution augmentation achieved the best results with an overall accuracy of 73.6%, and it outperformed both groups of models, the competitor multilingual BERT, as well as few short LLMs baselines based on GPT-4 and DeepSeek. These results confirm that language-specific pre-training and careful augmentation offer a superior strategy for the problem. And additionally, the performance relationship we observe between LLM-based solutions and pre-trained BERT-like models, the relationship we observe is quite aligned with findings from prior works and in other papers. This indicates that our approach performs comparably to the existing solutions. And finally, let's talk about limitations and future directions of work can be done. Firstly, we didn't fine-tune LLMs, an LLM, which can potentially also bring additional performance boost, considering the size of the models. Secondly, it seems that the back translation quality can be improved because it was conducted by using only one open source tool, LibreTranslate. And for example, we can also experiment with other tools, and in ideal scenario, to try DeepL or solutions from Google. However, it can be quite expensive. Additionally, expanding the dataset to cover more topics and content could further enhance models' performance, even with the same pipeline. And in conclusion, this study provides a solid foundation for advancing sentiment analysis for Ukrainian community, Ukrainian social media, and opens directions for future improvements. And also, it's need to be mentioned that we applied to the EU NLP workshop with these results, and now are preparing a camera-ready version. Thank you for your attention. I think we are ready to Q&A.
Would you like to start?
Yuri, many thanks for your presentation, and the work is nice, which I appreciate. I have a bunch of questions, so let's blitz on them. So, starting from the beginning till the end, could you please revert back to slide number 4?
Mm-hmm.
You mentioned here and 4. The chart which shows the number of publications, this one, the 5. You mentioned that research is quite saturated here. How did you measure and analyze this saturation?
I think it's like a personal feeling. It's not.
So it's a biased opinion.
Yes.
You would never mention saturation if you just rely on your biased opinion. How did you measure the popularity of Telegram? You mentioned that Telegram is the most popular social media tool.
For this goal, we used open social questionnaires. We used Opera social questionnaire as the source of
how many subjects were on the survey?
Oh, actually, I think we can watch if we follow the source, but it's statistically.
Was it your survey or just
not
publicly available results?
Publicly available results
from the
internet. Yes.
Okay, thank you. If we return back to the list of the seed papers you analyzed, we could notice that the seed papers are quite outdated. Why so? Why did you choose that?
I choose these papers because I want to make my citation network as wide as possible, and then select to form as big as possible, like a set of papers to
have more recent papers in your reference list in your diploma work.
Yes, there are a lot. This like a seed papers that from the starting point to extend our citation network.
What was the final collection of papers you analyzed in this work? I mean, in the statistics, what is the size, number of papers? What is the distribution by the years? What do you?
The papers we analyzed, the number of papers we analyzed is around 45.
Okay.
45, and most of them not older than 2021, 2022.
Okay. Yeah. Thank you. Slide number 9, please, where you mentioned bias, GPT 3.5 bias versus human validation. How could you be sure that it was the bias of GPT 3.5?
It's a good question.
On the other way around, it could be regarded as a bias by human annotators, isn't it?
Yes, it can be the case, but we also see. I didn't put this on the slide in the main part, but we also see the quite similar results in our research. For example, on the left-hand side, the classes distribution. There are the classes distribution of GPT for all.
I'm sorry, this just proves my hypothesis. The result repeats here as well.
Yes.
So why not interpreting it as a human annotator's bias?
But we are sure in human labels here. We develop a quite strict questionnaire for annotators and
I would better ground your answer on the kappa value
and achieved high result of the kappa. So a lot of people agreed on these labels and on this distribution. So you can be sure.
Could you please return back to slide number 11? Yeah, this word cloud. How did you extract terms for this cloud? You mentioned frequent terms.
Yes.
Are those terms, but not just words, in a word cloud?
Words.
And what's the difference between a term and a word? You just put terms there that forced me to think that you are an expert in terminology extraction.
Yes, this just words. The method work. The method we use to build.
So it's an off-the-shelf method for building word clouds, isn't it?
Yes.
Okay, thank you. Who were your annotators? Slide 13. You didn't mention how many annotators did you have?
I was an annotator, and I have a team of 4 additional annotators that have agreed to join our project.
Who were these people? I mean, in terms of their qualification for the job.
This is my brother, Vladimir, and colleagues from my work, not professional linguists, but the data professionals.
Did they have any background in sentiment analysis? Except you, of course.
No, they didn't have any prior specific professional experience in sentiment analysis or other linguistic field.
That reinforces my interpretation of the human bias in your work.
Okay.
Let's go to back translation. Did you back translate individual words, or was it at sentence level?
On document level.
Document. So you translated documents.
Yes.
And how did you translate it to original? Manually? You have an English version of a document and a Ukrainian version of a document, for example.
And then we use English.
How did you map the chunks, the unigrams in the text between languages. Did you do this manually or
this was a manual check on a subset of samples after the
how many
preparation.
documents did you process in that?
200 as for back translation and for
what was the average size of those documents?
From 200 to 300 symbols, if we
short text, okay.
But all texts in the data set are in this range.
Yeah, you didn't mention, by the way. Why the accuracy, I mean, in terms of F1 score, is so much smaller than that for the state of the art for English? Did you try your setup for English sentiment analysis just to align?
No, we didn't test this, but these results coincide with other researchers for European languages, especially for Lithuanian and Hungarian. I think that there are two reasons. First is that the dataset quality. Our dataset is quite small. Despite we put all our best effort to make it as big as it can be. And also, I think that, as you mentioned,
human bias.
Maybe some human bias, but if we check the results with, for example, on the slide now with other research for Lithuanians, we can see they used a smaller model, Distilbert, but achieved
slightly better
results. Okay. Yes, and Hungarian, Polish, and there are complex research about these three languages. The researchers used also BERT and achieved even worse results than ours. So,
but they're better in Llama 2.
Yes.
This is F1 score, yeah?
Yes, yes. Okay. Macro averaged.
Perhaps my final question. Sorry for being that long. My final question is, could you please sentence your contribution in this work? What do you defend?
I think that I established a benchmark for that can be used for further research in the field, and created a publicly available open data set that is also needed to establish such a benchmark, and provide some methodology tested the most popular approaches to the problem. So it's like a good starting point this for Ukrainian language in this field.
Okay, thank you very much.
Oh, sorry. Anybody else from the... we started a few minutes later, so we have still around, let's say, 5 minutes for questions. So
thank you very much for your very interesting project and your very interesting talk. Could you clarify just one moment for me? Maybe it's not relevant. Some moment associated with calibration of the NLP model. Why is it so important? And next question, it is in a property of the model, or we can recalibrate the model to improve this? Maybe it's not relevant.
Collaboration is important because the performance results, when we measure, for example, one score can be quite good, but it can be, but these results can be not so trustworthy if the model isn't calibrated enough, because if we analyze confidence scores, they can be a little bit messy and not coincide with expected likelihood of some outcomes that model provide. So yes, this is important. And the second part of the question,
if model not calibrated enough, so can we recalibrate the model? Are there some methods?
We can try. This can be done by using or more data, or it can be or the architecture, or we can use this model with another architecture. Maybe some model is not appropriate for our case, for example.
Okay. Thank you so much. Thank you very much.
Thank you too.
Thank you, Yuri, for a very nice presentation. I have a couple of questions. You mentioned that your data set contains posts in Ukrainian, in Russian language, and mixed. Did you analyze if there is any difference between sentiment distribution between these two languages?
It's a good question. I didn't remember if I put this on the... No, I think no. But yes, we did it. And we see some negative bias, negative skew demonstrated in text in Russian compared to code switched and Ukrainian. This is maybe the most remarkable observation that I saw.
Can this explain the difference between performance?
I think not. The difference not quite too strong. So I don't think so that this is a reason why, for example, mbird performed worse than Roberta trained on Ukrainian text.
Mm-hmm. And also, you said that the majority or main source of your data set was news channels?
Yes, news posts and comments under these
okay,
posts.
Also comments.
Mm-hmm,
because news posts typically are neutral. Just
yes.
Convey information.
We can see some small part of examples of texts here and annotated disagreement across edge cases. And this is quite representative. It represents
and also, as you said, the mean length of the post is about 200 symbols, which probably are 20 words. I wonder how within these 20 words you could detect mixed sentiments, because it's probably quite unusual to have both.
It's a good observation. We see a clear skewness to the longer text in case of mixed sentiment. So yeah, mixed sentiment needs more space to be fit in. You can see here mixed sentiment, and the distribution is quite moved to the right.
Okay, thank you.
One question. Maybe final question, because we have limitation in time. My question is, we have, for today, we have a lot of different type of records from front line among different subdivision of Russian army. How to transform your approach to understand these talks? So not sentiment, but semantic analysis. How to transform your approach for understanding of semantics, these a lot of small talk, medium talks between subdivisions of Russian army. That is a double purpose system.
I think we need here an additional data set and additional labeling, because the framework presented cannot be used directly for this task. But overall approach can be used if we will have labeled data with. I think it could work.
Okay, thank you, Yuri.
Thank you, Tim.
Let's move on. The next student is Wladислав Radchenko, and he was advised by Nazary Drushchak, the graduate of our program, and he will be presenting his work entitled Improving Name Entity Recognition of Low Resource Languages using Large Language Models, a Ukrainian case study.
Oh, I'm sorry. Stole the mic. Can you hear me well? So, good morning. This thesis investigates strategies for improving named entity recognition for low-resource languages with a specific focus on Ukrainian. One of the central goals of this work is to explore how large language models can be effectively used when annotated data is limited or unavailable. This research was conducted under the supervision of Nazariy Drushak. So here's the structure of my talk. I'll go all the way from the motivation and background to the conclusions and future work. Starting from the basics, named entity recognition is the subfield of NLP that focuses on extraction and classifying entities like people, organizations, locations within the unstructured text data. A simple example is illustrated on the slide. Two types of entities are identified. It's locations and person. So NER has a wide range of practical applications. It's essential for data anonymization, especially in sensitive domains like healthcare, where PII-based data must be masked. It powers information extraction systems used in search engines, digital assistants to structure and retrieve relevant content. And in social media monitoring, NER helps businesses to detect and categorize mentions of people, brands, and organizations in real time. As NER is a fundamental task in NLP, over the years, many approaches have been developed, from rule-based systems to modern deep learning models. What we need to know is that most NER benchmarks today are dominated by transformer-based models, so that's where I focus my work. Transformer models use this self-attention mechanism to capture contextual information, making them highly effective for tasks like NER. Encoder-only models such as BERT, RoBERTa, and DeBERTa dominate current benchmarks. However, their strong performance depends on access to large, high-quality annotated datasets, which poses a major challenge for Ukrainian. So that in Ukrainian NER, we have two major challenges. First is the data scarcity issue. There are very few high-quality annotated datasets available, especially when compared to high-resource languages. And the second is linguistic complexity. Rich morphology and flexible word order make entity recognition even harder. So thinking about real-world applications, let's focus on two key low-resource scenarios. First one is when no annotated data available at all. This can happen when we need to extract specific entity types, for example, law titles, nationalities, infrastructure sites, but there is no annotated dataset exist yet. Still, we have few options to start with. First, we can try knowledge-based methods. It's a simple heuristics like suffix rules, dictionaries, or regex patterns. Next, we can turn to generalist models like Gleaner, which come as pre-trained models that can easily extract common entity types without any additional training required. And finally, we can explore prompting LLMs using models like GPT to extract entities directly using prompts. So the second scenario is when we have some annotated data, just not much of it. In this case, we can try two practical solutions. First, we can apply transfer learning, taking a multilingual model and fine-tuning it on the small labeled dataset we have. This lets the model adapt quickly using existing knowledge from other languages. Then we can use silver standard annotations by running a strong model over large unlabeled corpus to automatically generate additional training data. Together, these approaches allows us to scale NER systems effectively while minimizing the need for costly manual annotated data. In this work, we explore all mentioned approaches with emphasis on large language models, as they offer several key advantages. First of all, they are pre-trained on huge corpora of language so that they understand language well just out of the box. They are also task and domain agnostic, meaning that they can transfer across languages and use cases. And importantly, for low-resource setting, they support zero and few-shot learning, reducing the need for large annotated datasets. The idea of LLM utilization for NER has gained a lot of attention over past 2 years. Recent studies like GPT-NER and PromptNER show that large language models can match or even outperform supervised baselines, especially in low-resource or few-shot scenarios.
Throughout our study, we outlined the following research gaps. First of all, while LLMs have been explored in low resource domains, most of them focuses on English, and their use for Ukrainian remains underexplored. Second is that much of our progress relied on the proprietary LLMs, and open source alternatives are barely explored. And third limitation is, third research gap is that the data is limited for Ukrainian. Based on these gaps we identified, this thesis sets out to achieve three main objectives. First, to adapt large language models for Ukrainian air with a specific focus on exploring how these models perform in low resource setting. Second, to promote open source solutions as alternatives to proprietary models like GPT. Open source models are more accessible, easier to reproduce and deploy in production. Third, to construct a silver standard dataset for Ukrainian air using UberText 2.0 corpus. This helps us to address the lack of annotated data issue, especially in informal and social media domains. To highlight the differences in data availability, I've compared few high-resource datasets and Ukrainian datasets. High-resource corpora like Ontonodes, FewNerd, and NNE offer broad coverage across many entity types and domains. They are commonly used in English benchmarking. For Ukrainian, the picture looks a bit different, a bit more limited. NER-UK 2.0 is the most comprehensive public resource with 13 categories and manual annotations. However, it still lacks the scale and domain diversity of its high-resource counterparts. Other datasets like WikiN or SlavNer are either weakly supervised or support only basic entity types, usually person, location, organization. In our research, we use NER-UK 2.0, the largest manually annotated Ukrainian NER corpus. It includes 22,000 labeled entities across 13 categories. It's currently the strongest benchmark for Ukrainian NER. As shown in table, common categories like person, organization, and location dominate the distribution. Meanwhile, other like time and doc remain underrepresented, presenting challenges for model training, which is a good in our case, since we'll be able to examine how well large language models can handle low resource entity types as well. We explore 4 experimental tracks to understand how well different strategies perform under low supervision conditions, under low resource conditions. First, we established a strong baseline by fine-tuning encoder-only models. Then we tested low supervision setups, prompting LLMs using zero-shot, few-shot, chain-of-thought strategies, and using generalist models like Gleaner with zero-shot setup. We also applied supervised fine-tuning with LoRa adapters for large instruction-tuned models, which performed the best in prompting results. Lastly, we created a silver standard dataset and used it for hybrid model training. This setup allowed us to compare the trade-off between supervision levels, model types, and training resources. We evaluated all models using the same methodology as in the original NER-UK 2.0 study. The main metric was selected as the weighted F1 score. For span matching, we used an exact matching strategy, meaning predicted spans had to align perfectly with annotated ones. All evaluations were conducted using SPACY framework to ensure consistency and reproducibility. We selected models from 3 main groups: proprietary LLMs, open source LLMs, and encoder-only models to cover a broad spectrum of architectures and capabilities. This setup allowed us to fairly compare different strategies for NER under varying level of supervision. To access LLMs fairly, we first established a strong baseline using encoder-only models trained under full supervision. These models provide a reference point for comparing low supervision and generative approaches. We tune hyperparameters first on the validation split using early stoppage, then retrain on the full datasets. Since outputs are token-aligned and structurally valid, no extra post-processing is needed during the evaluation. All encoder-based models showed solid results, with Roberta Large NER slightly outperforming the rest of the models, reaching the highest F1 score of 0.89. It was therefore selected as the main baseline throughout the study. During this process, we also discovered a data leakage in the NER-UK 2.0 study, where the test set was mistakenly used for early stoppage. That's why we had to retrain their model. We corrected this by retraining this model with a proper validation split. On the lower end, modern BERT large outperformed with F1 score of 0.76, likely due to its monolingual nature and limited exposure to Ukrainian. This underlines the value of multilingual pre-training when working with low-resource languages. In the next experiment, we simulated a low-resource setting by using LLMs without any training. We applied zero-shot, few-shot, and chain-of-thought prompting strategies. Prompts were dynamically generated for each sentence and structured using the chat templates. We utilized Pydantic to validate and parse model outputs. Since LLMs can produce noisy or even hallucinated outputs, we designed three-stage post-processing pipeline to clean and structure predictions step by step. We start with the bronze layer, where we collect raw outputs as is. It may help us to understand how model behave out of the box. Then comes silver layer, where we align prediction spans to the original text and remove invalid formats, ensuring structural consistency. Finally, in the gold stage, we apply rule-based filters tailored for each entity types based on our error analysis on the first stages of the research. For example, we discard person names that start from lowercase letter based on the knowledge about this data type. Now let's see how well prompting strategies actually performed. We can clearly see that few-shot prompting consistently outperforms zero-shot, while chain-of-thought prompting showed no reliable improvements, suggesting it may not be ideal for NER. Post-processing significantly boosted the results. Most models produced nearly correct outputs, needed only minor normalization to become evaluation ready. Among open source models, Geometry reached the highest score of 0.71 F1 score, closely approaching to GPT-4o at 0.72, which shows a minor gap between open source and proprietary models. Then we evaluated generalist models, zero-shot capabilities, using pretty similar pipeline, however simpler. These models are built specifically for NER and return entity spans directly. Therefore, no prompts or span alignment is needed. This makes them fast and easy to integrate in low-resource setup. Despite their simplicity, generalist models still perform competitively, achieving up to 0.67 F1 score in zero-shot mode. This makes them a strong choice when speed, simplicity, and ease of deployment are more important than maximizing accuracy. To evaluate how instruction-tuned LLMs perform with task-specific training, we also applied supervised fine-tuning using LoRa adapters through the Onslaught framework. First, we tuned the hyperparameters on the validation split. Then we retrained the model on the full training set using the best configuration. The rest of the pipeline reused the prompting setup described previously, with one change. We skipped the gold post-processing stage during the evaluation, since it showed little benefit to the results. All LLMs achieve comparable results, with Geometry reaching F1 score of 0.888, nearly matching the encoder-based Roberta Large NER. While performance was strong on frequent entity types like person and organizations, results dropped on rare classes, such as time and MISC, showing that larger models alone does not solve the data sparsity issue. Overall, no significant advantage was observed in fine-tuning LLMs compared to encoder-only models when annotated data is limited. As a final step of our study, we aim to expand Ukrainian NER coverage beyond the formal domains. We focused on the social media portion of UberText 2.0 corpus, an entity-rich yet underrepresented source in other datasets. The pipeline included several pre-processing steps. First of all, its deduplication, noise removal, language filtering, and white space normalization. We took our best model, Roberta Large NER, and used it for sentence-level inference to label the annotations and saved it in EOP file format and publicly published it under the LangUke organization. The scale of UberText NER Silver is substantial, over 2 million sentences, nearly 45 million words, and more than 4 million labeled entities. Making a more detailed breakdown by entity type, we can notice that categories like location, organization, and person exhibit high redundancy, illustrating the frequency with which key geopolitical locations, institutions, and public figures recur throughout the dataset. To better understand the content of the silver dataset, we analyzed the most frequent entity surface form by type. This revealed a strong presence of terms related to COVID-19 pandemic and the full-scale invasion of Ukraine. This indicates that the dataset not only reflects the rich linguistic patterns, but also captures recent and relevant events, making it highly suitable for training models that need to process real-world data. Once the dataset was gathered, we moved on to training of the final model. First, we combined two sources, high-quality gold standard annotations from NER YUG 2.0 and high-coverage silver annotations from UberText NER Silver. Due to the scale of silver corpus, we filtered it a bit, retaining only sentences with at least one unique entity, and with random sample of 80,000 no entity sentences to reduce training cost while preserving span diversity. We then trained the model using the same spacey pipeline, applying early stoppage for parameter tuning. The resulting model achieved F1 score of 0.944, setting a new SOTA model for this benchmark. Importantly, this hybrid approach improved recognition of rare, previously underrepresented entity types like dog, art, and time. These results demonstrate that combining clean gold annotations with large-scale silver data is effective and practical strategy for low-resource NER. Here we can see the highlights across all the experiments that we've done. First, encoder-only models like Roberta Large NER showed strong results in full supervised setup, achieving 0.89 F1 score and serving as a solid baseline. Then we moved to prompting-based evaluations. Few-shot prompting worked well for both GPT-4 and Gemma 3, reaching F1 score of 0.72 and 0.71, but required post-processing and was expensive. Generalist models gave decent zero-shot performance without training or setup, making them useful when compute or data is limited. In supervised fine-tuning, Gemma 3 reached 0.888 F1 score, nearly matching the encoder baseline, but did not show any clear advantage over Roberta Large NER. Finally, we introduced Roberta Large NER YUG, a new model trained on both gold and silver data. It achieved 0.844 F1 score, our best result, significantly improving underrepresented categories like time, dog, and percent. So to wrap this up with our main contributions of this work, first of all, we explored how large language models behave under different levels of supervision, from zero-shot setup to supervised fine-tuning. Then we benchmarked models across different types, including encoder-only baseline, open source LLMs, and proprietary options. We also created UberText NER Silver, a silver standard dataset focused on social media domain, which is often limited in existing resources. We developed a new state-of-the-art model for Ukrainian NER, trained on the combination of gold and silver annotations. And finally, this research was formed the basis for the paper accepted to UNLP 2025, further validating the significance of our findings. Looking ahead, we see four promising directions. First of all, we want to explore how to adapt LLMs for encoder-style architectures and repurpose them as text encoders through the modification of enabling, for example, bidirectional attention. This could help make token classification more efficient. Techniques like LLM2vec are a good starting point here. Second, we may try and reinforcement learning techniques to better align the NER-specific objectives, models with NER-specific objectives. And third, we can focus on expanding our existing data resource, for example, by labeling the full NER-YUG, by labeling full UberText 2.0 corpus. Finally, we can refine our silver standard annotations using advanced techniques like CA-minor, multi-nerd, wiki-neural. This could help to reduce noise and improve label consistency in automatically generated data. Thank you for your attention. I'm happy to take questions you may have.
Let's now start from this side. Anybody have questions? Okay, so I will start then. A very quick question. Is your dataset published?
Yes, it's published under LangUC organization.
Mm-hmm. And you also mentioned that your prompts were automatically generated. Could you please elaborate a little bit more how your prompts were generated?
Could you specify on which slide it was mentioned?
Well, I don't remember, but you were speaking about evaluating large language models, and you said that your prompts were automatically generated.
Yeah, I guess you're referring to the slide with. So I said they were dynamically generated. So we have the blueprint, which expected only sentence to be pasted. So this is how it was dynamically generated. So that was the whole point. So in this blueprint, dynamically were pasted the sentence for which we needed to receive inference. So all of the few short examples were stale in each example.
I see. Yeah, I'm also interested about like real world applications. For example, let's imagine you are designing a system, and one of the components of that system is a module that needs to do name entity recognition. So what will be your like go-to solution to solve that problem and integrate it into your whole pipeline? Will it be a large language model? Will it be Roberta or anything else?
It depends on the condition in which we are being. So if we do have labeled data set, then utilization of encoder-only model, which will be the tested and good solution with good efficiency and minimal cost. If we are working with under low resource conditions, and for example, we do not have data set and we need to extract nationalities, and there is no publicly available data set for this problem, we would need to look at our compute resources and into our priorities. So if the priority is maximizing the accuracy and compute is not a problem, then we would move with large language models since they yield the best result in this setup. If we have problems with compute, then we would probably move with more lightweight solution like cleaner model. They are easy to set up and pretty cheap to utilize. And if we do have finances and do not have compute, we can utilize the proprietary models, which would be a great solution and pretty easy to integrate.
Okay. Anybody else?
Thank you for your presentation. I want to start with the title. You mentioned Ukrainian as a low resource language. So how do you justify this statement?
Yeah, thank you for the question. It's a bit tricky. I have a separate slide for it. So I took this quote from one of the well-cited papers. So it can be understood as less studied, resource scarce, less computerized, less privileged, less commonly taught, and low diversity, among other denominations. So the problem of this definition is that it does not have any thresholds, specific thresholds. So it's a bit difficult to tell you for sure whether the language is low resource or no. But we can identify few clear signs that may allow us to do this decision. So first of all, how many publicly available data sets we have, whether the entity coverage is limited, and whether how good is support in pre-trained models, for example.
Okay, I see, but I think that this definition and justification is a bit outdated because for recent years in Ukrainian language, we have a bit of extra resources, data sets, and I think it could be qualified as a medium resource language so far. Okay, but then can you get back to the table? I cannot recover this slide, but where I compare the models, and there was Mamai LLM.
Yeah.
Yeah, probably this one.
Yeah, it is.
Okay, so we have Mamai LLM as only one Ukrainian LLM here.
No, IA as well.
IA, okay. So what's your justification? Why this So if you compare MyLM based on Gemma 2, and Gemma 2 is like, if you have this first column, left column is 0.42 and MyLM is 0.36, right? Zero shot. And on other rows, a bit the same difference. So what's your justification of this difference? Because MyLM is based on Gemma, and we see here that Gemma is per se is higher than MyLM. And
Yeah.
we assume that MyLM is pre-trained on Ukrainian data.
So I was surprised by this fact as well, that the performance is substantially low in comparison with Gemma 2. So I can only assume, and I have only one assumption, that maybe it was pre-trained on only non-NER data. That's why it just forgot how to perform it properly, or something like that.
So you did not investigate deeper. I mean,
no.
Have you tried to read something about MyLM? Okay, thank you.
Thank you very much for your presentation and for your results. I have a question about prompting based strategies. I'm looking for your abstract. I can't associate with this slide. You used zero shot, few shot, and chain of thoughts prompting. Could you clarify, as usual, chain of thoughts associated with reasoner models? Can you, is this approach gives you better results, or when we compare it with zero shot or few shot prompting?
So compare different results of different prompting.
What's better, zero shot or chain of thought in this in your?
Well, in my work, from the results, we can clearly see that zero shot outperforms the chain of thought. My assumption is that the chain of thought, like the models were already somehow trained on the NER data and do understand this task out of the box. And then they do not need any additional like reasoning steps what to do. And when we add them, we just confuse the model. And in contrast, what it needs a better understanding of entity types in order to understand what to extract. And that's what gives zero shot and few shot setup. That's why few shot is the best strategy in my opinion, from the results.
Okay, thank you very much.
Thank you for a great presentation. I appreciate it very much. I have a few questions for you. My first question is about comparing your results to the known results which are available at multilingual leaderboards on there. Have you done that? Did you look into the leaderboards or named entity recognition in multilingual settings?
No, we did not.
Why?
So do I understand it correctly that the goal of this comparison would be to try our model on different languages?
No, just to understand how far you are ahead or behind the state of the art in multilingual.
We are aiming for the local benchmarks and for the Ukrainian specifically. That's why we focused our research on the local, the biggest benchmark for Ukrainian language, NERYUK 2.0.
I would suggest that you look into multilingual because it may show you the gap.
And that's a reasonable question. If we would want to aim for the multilingual, I would assume that we would rather go with SlavNer dataset, since it contains multiple languages together, Slavic languages. And that would be just slightly different direction. I would assume if we
There's also a Slovenian dataset which has 11 languages for named entity recognition. Just take a look. Okay. One else. Could you please go forward to your slide 32? 32, yeah, this one. I'm sure that all the examples you have here are named entities. How would you denote a named entity, please?
The node entity is either word or some connection of words, which can be classified as the entity of specific category. Like, for example, the authors of the dataset give the specific meaning, which may contain the words. And if words contains this meaning, then they can be classified as entities of these categories.
I'm looking at your number 4. It says Golova. Would you really recognize or interpret this word as a named entity?
It may be голова державної комісії, which...
It doesn't say голова державної комісії, I'm sorry.
Okay, one more clarification that it is a silver standard dataset, so the quality of this dataset is not perfect and it should be further refined, and it has quite a lot of mispredictions and just hallucinations probably. So that's in our future work to apply some advanced data refinement techniques and apply manual annotations to improve the quality of the dataset. Currently, it's just the frequency, like the frequency analysis of different entities.
Do you think that BPLA is a named entity? A name of an instance of a class? And all the times, time intervals you mentioned in the second row.
It is an arguable point because MISC is the hardest category in this data set since it contains the wide range of...
This is why I'm pointing you to these discrepancies, because this will have a straightforward effect on the quality of named entity extraction. So you have to have a sort of a formal understanding of what a named entity is in order to make a reliable annotation, even in silver settings, and even more in silver settings, isn't it?
You are correct. However, we did not change the predictions at all. So as we utilized the predictions which were done by the model, and we did not make any refinement yet. Therefore, it's expected that there will be some hallucinations and misclassified entities.
So you are just saying that we cannot trust the results of this way?
Definitely, it's silver standard. That's why
no, I'm not about silver standard. I'm about the tables in your slides.
I mean,
from 22 to 28.
22.
I mean the performance slides, the tables.
Okay.
So we cannot trust it.
Why?
Because you do not know what a named entity is. I mean, formally, your model does not know. You just rely to its interpretation as a black box.
The meaning of...
Which could be spoiled.
The meaning of
named entity.
Named entity is described in the Neryuk paper, and we can get an understanding what each entity type means from it. However, there are some edge cases, and even for human, it is difficult to tell whether BPLA is MISC or art, etc. So there are some cases, and I'm not a linguist to tell for sure.
Okay, thank you very much. Could you please go forward to slide number 34?
Yep.
What does overall mean here? Is it a mean average? Or it's an
weighted F1 score.
It's way overall?
Yes, for all categories. Aggregated.
How do you aggregate it?
Like weighted F1 score assigns more weight to the more presented categories within the dataset. That's the metric that we were inherited from the previous study.
Got it. Sorry. And finally to the contributions. Contribution slides.
Yeah, sorry.
Yeah. No, the first contribution was we explored. Yeah, this one.
Yeah.
Exploring is an activity. Is an activity a contribution? I expected a result here.
Those explorations leaded to results. So we could say that we validated different approaches and compare them together in order to understand which performed better and which performed worse in different conditions, supervision, setups, and on different models.
I'm just picking the wording here.
Work could be better.
So it's in the first place, meaning that it's the most important contribution in your work, which is the process, not the result.
Yeah, I agree. It
diminishes the value of your work. Okay.
A bit.
Thank you very much.
Maybe a little question.
Yeah.
From my point of view, your approach has potential possibilities to improve token label classification. Which one, from your point of view?
It depends in which setting we are looking at the problem. If we are looking from the full supervised perspective, then I would look into the direction of the first point described in my future works. It's repurposing of LLMs for text encoders. Now we benchmarked all LLMs and see which one will be promising for re-engineering, let's say.
Okay, and let's have a last question from the audience.
Yeah, question from the audience. From common sense, we know that LLM in general could perform a human level, like labeling tasks or other things. So what is your explanation for a gap between all LLMs results that are around 70 to 80% and a BERT result which is 94%, I believe. So like, is it LLM failure or yours in terms of NER task for Ukrainian language?
So you're asking why such a big performance gap between low resource?
Why there is a huge gap between LLM performance and BERT performance for NER task in your case?
Well, we need to understand that the BERT was trained on the full data set, and the huge performance can be observed only in comparison with low supervision setup, which implied that we utilized only 5 or 3 examples in the prompt. That is why it's not like really fairly to compare those different setups. If the BERT has only 3 examples as Roberta did, then we could tell about the efficiency here. But in the full supervised setup, we can see that the difference is minimal. The difference in 0, 0, and 2 of F1 score. As you can see here, Roberta has 0.89 and the geometry has 0.888.
Okay.
So we have 14 minutes break and then we will start again. Okay, so it's almost 11 a.m. It's already 11. So let's move on with the next student, Vitaly Borodavko. He was advised by Artur Kulian, and his work is entitled Hybrid Tokenization for Ukrainian Language using Morphemes and BPE. Vitaly, start whenever you're ready.
Ні, я дивлюсь, чи нормально. Yeah, okay. So ladies and gentlemen, thank you for the opportunity to be here today. So my topic for this master thesis is the hybrid tokenization for Ukrainian language. So shortly, we will walk through the thesis plan. So firstly, we will discuss the tokenization, what it is and how it is applied. Next, we will go through the motivation of this research. After that, we will take a look at the most important related works. For this topic, we mentioned some morphology of Ukrainian language in general, and also the tokenization in LLMs itself. Then we define some research gap that we could identify during this research. Then we define the most important questions and problems for this master thesis. Then we take a look at the tokenization with morphemes as an application. We will move on to the experiments and results of the evaluations. And then we finalize it with the conclusions, some limitations, and proposal for future works on this topic. So let's start with the introduction. So what is the tokenization? As we might know that in NLP, we work with the text, and text cannot be directly processed by any actual model. So we need to sum this additional layer. And previously, before LLMs, we used some applications like TF-IDF or Word2X that actually somehow represent text into the numerical format. With LLMs, we need this processing tool. So what is the tokenization itself? It is the process of converting text into smaller units, numerical, that is called tokens. And these tokens is actually what the model actually works with. So we have this additional layer. It can be set up independently from the exact model task, or it can be directly used with the exact text corpuses that was used for our task. It's actually due to the most important things. It do encoding, so we convert text into the sequence of tokens, and the reverse process of decoding when the model generates the output, it actually generates a numerical sequence that need to be mapped back to the text. It will be understandable by people. The most spread application is to the tokenization. So the first one is a character level. So we just split all the text into characters, separate tokens. It has some advantages. So it can handle any input. It's really small regarding the vocabulary size, because actually all we just need is the unique symbols. So it makes the vocabularies really compact. But of course, some cons. So we completely lose the semantic structure of the text. So we treat it like separate characters that actually don't represent any semantic meanings. With that, we create really long sequences of tokens. So actually, if we have a text with 1,000 elements long, we have 1,000 tokens, which is bad, and we'll discuss it a bit later. And yeah, in general, models need to handle longer sequences of dependencies, and it's add additional complexity on the training and the size of the models itself. The next approach is a word level. It is something that, as for humans, might be more representable. So we have a higher semantics as we operate in words. We need, in this case, need to store much shorter sequences of these tokens. And as I mentioned, it aligns with the human understanding. Though there is some disadvantages, is we actually really extend the vocabulary size, because now we need to represent each separate word explicitly. So actually we need to store the entire vocabularies that we need to operate with. it becomes not so flexible as we cannot handle words that we didn't see during the training phase. And it has a poor generalization on the morphology rich language. It is connected with the vocabulary size. As for example, in some languages, words might be changed by some forms and representations, and for each of them, we need to store additional words, and we'll also take a look at the example of it a bit later. Something in the middle is subword tokenization. So we don't use the entire words, but though we don't fall back to this meaningless characters representation, now we have a more efficient vocabulary size. So we split words and sentences into some meaningful tokens. It is a better representation of morphologically rich languages. And here we can handle words that we didn't see during training, as, for example, we might have some parts that actually might compensate the lack of this word in the vocabulary itself. And from cons, of course, it is more complex encoding process. So we cannot just use some split by white spaces or something like that. We need to add some heuristics here. And another problem is that it might produce some unnecessary splits, and these splits between these tokens might be unnatural, and for people, they might not be logical. So English language is leading language in the development of language generation tasks. So the most of the researchers and the first language models was built based on the English language. And here is the visualization built with the tick tokenizer application. And here we can see actually how language models treat the text. So we can see that here almost all words are treated like separate words. So it's like closer to word level understanding. And besides one example of tokenizers, all of them are really understandable by humans. So that's how actually human operates. But at the same time, we might also note that it is not that flexible as it could be. So we have a word success and a few other formats of representation of this word. And we can see with these colors that actually the word success and successful is two different tokens. What it leads to is we actually enlarge the vocabulary size. But in this case, we might just save the word success, all the possible prefixes and suffixes, and in general, we could represent all these versions without storing them explicitly. And now this is the example. I'm not sure it is well visible. So here is the example of how it works with the Ukrainian language. So we made the experiment with different models, and I don't know if you can see it, but many of them, they are kind of very chaotic. So some of them represent the full text, some of them actually represent a single character. So they're not stable in the representation. And it also loses some semantic of the exact character. And one important note is here with the GPT. We can see that actually during the history, the representation ability is improving as we need to use less tokens to represent the same text. Now we'll talk about the motivation for the research. So Ukrainian language is underrepresented in the training of language models, as they are training on the corpuses that are parsed from the internet, and the representation of English is much more bigger than the presentation of Ukrainian text there. That is why it is directly influence the performance of language models. From that, we get higher cost of processing of this underrepresented language, as we need to process more tokens to actually process the same text lengths. We don't really understand how to handle morphological complexity. So in case of the English, where words and parts of the words are pretty concatenative, we cannot apply this directly to Ukrainian language. It is more complex morphologically. We also want to check, is it possible to reduce the vocabulary size just by replacing the approach to the tokenization? And maybe it can become the new optimal tokenization for processing Ukrainian language in general. Now, about the related works, it turned out that not many researches was made for Ukrainian language, and that was a problem. So we don't know which tokenizer is more optimal for Ukrainian, as we don't have this kind of research. So for processing this topic, we need to kind of step back on a more kind of general layer. So we need to look not on the Ukrainian language itself, but maybe to try to find languages that are similar to that, and to try to find some insights from there and try to adapt them on Ukrainian language. Here is the linguistic topology. That is actually the science that structure language into the groups and try to find the common characteristic there. In this topology, one of the way of splitting languages is the by morphology. So languages are either analytical or synthetic, and the difference is actually in the constructing of the language. So in other Latin languages, one morphemes actually represent the whole word. So we don't have this variability. These parts are independent, and we use them separately like a bricks. In case of the synthetic languages, they have more groups. They are agglutinative, fusional, or polysynthetic. And the difference is that how parts of this text are logically splitted. So for example, with agglutinative language, one morpheme represents one grammatical feature. It is easy to segment, it is easy to stack them together. They don't have these changes when we actually concatenate them together. Whereas in the fusional language, when we want to change word form, we might actually change a few semantic representations. So it can be, for example, we can change one ending, and here is actually the example of that. So we might have one word, обігрівати, and when we change only the ending or even suffix and ending, we can change completely the meaning of the word. Whereas with the agglutinative languages, with the example of Turkish language, we can see here that they are easier to represent. So if we want to add some semantic, we need to add just another token, and it won't affect the part that is already there. So this kind of languages is much easier to represent in comparison to fusional language, and Ukrainian language actually belong to this group of fusional languages. Yeah, so now regarding the tokenization in LLMs, advisor of this work has a previous researchers that actually studies the cost and fairness between the languages. For example, Italian language is 1.6 times more expensive in processing in comparison to English, whereas the Ukrainian is 3 times more expensive. So if you have the same sense that you want to pass to the language models, making it with Ukrainian language costs you 3 times more, which is unfair, and we want to kind of reduce or try to reduce this bias towards English language. And also, as we process more tokens, it takes longer time, and of course, we can fit less context into the same context window. Another important step in this research is also previous work of Arthur Cullian. So what they actually did is they tried to kind of add new Ukrainian token into the languages that were trained on English. And it turned out that these tokens can be adapted. So language model that was trained on English, it might have some understanding of the language, and this understanding can be transferred to the Ukrainian with adding some tokens and fine tuning. And actually here is some plots that actually shows that after some training steps, the usage of new Ukrainian tokens increases. So this adaptation is a thing and can be used further. The problem is that morphemes the usage of morphemes in other languages are not stable. So for some languages, they do show the increase of the performance, and for some, they don't. Even within the same language group, there is a not stable increase in performance. And here is I guess, the key previous research that will be used for this work as well, is how to apply these morphemes to the tokenization problem. So we actually can create the morph table that is actually the dictionary. And for each text, we try to find the match inside this morpheme tables. And if the match is if the match was found, we use this morpheme itself. If not, we just pass it to the standard BPE tokenization that might be less optimal than splitting by the morphemes. Yeah, so the research gap, we don't have the optimal strategy for Ukrainian language. We don't understand the impact of the tokenization on the ability to represent Ukrainian language. And it would be good to understand that if this representation may reduce the sequence length of the tokens. So the question is, can we have the better representation of Ukrainian language? Does it have the impact on the LLM performance? And can we actually improve this representation without degrading model performance? So we need to process existing resources of language morphemes. Then we build the actual vocabularies. Based on these vocabularies, we formulate the tokenizers. We perform statistical analysis with these morphemes compared to pre-trained tokenizers. And then in the end, we want to train the model and compare their performance with both of these approaches. So with those resources, it turned out that we don't have actually existing tokenizer for Ukrainian language. We also did not have the existing vocabularies of these morphemes that we can be used. We have a few digital versions of Ukrainian vocabularies, and they were private and shared with us for making this research, so they are not open sourced. The best we can find is the printed or scanned versions of the morpheme vocabularies. Actually, that is basically images, so they cannot be utilized just from the beginning. That is what we could find. So actually, two open sourced, two published sources. It is actually the two vocabularies published in 2009 and 1981. So they are pretty much outdated as a language constantly developing. In general, they contain 40 and 120,000 words. And the last one is a database collected by the Department of Ukrainian Language and Applied Linguistics in University of Shevchenko. That was shared with us privately for this research. Here's how actually the words represents. So they are split by the slashes into these morpheme parts. What we did is we need to actually convert this conversion that does not contain a text layer into something that we can process. So we applied optical character recognition. Among the approaches that was used, the marker is the best one working for our case. The quality of these printed sources are not perfect, and we also have some mistakes during the recognition. So we try to apply correction with GPT-4o model. It turned out that it's not enough to actually use them, so they still have a lot of mistakes. So we use human validation for the correction. So what we have is actually 3 vocabularies. They have almost 18,000 for the first one, almost 8,000 of morphemes, and almost 30,000 of morphemes corresponding to the vocabularies. And in general, we can see that the fertility rate is actually indicates how many tokens need to represent a single word in Ukrainian language. Here's an example. So with this vocabularies, we try to represent the same sentence with different tokenizers that was pre-trained with Gemma model, with the Mistral, and actually with vocabularies that we created. And we can see that actually they are not, they do not perform better than, in this case, almost all models that are presented here. So we might make a conclusion that this representation might not actually reduce the size of the sequences. It may improve the logic of the splits, but definitely it might not work in case of the reducing lengths. What we did here is we tried to use the default BBE approach and some linguistic vocabularies.
I'm sorry, you have 1 minute late. I give you 5 more minutes, but please be more concise so that we could evaluate your work.
Okay, thank you. So moving to the model, we decided to use the UberText for validation. We have 2 approaches of training from the ground with the GPT model, or to fine-tune existing model, which is actually more complex, as these models are they are large, they are pre-trained, and fine-tuning might not reach the conversions that we want, but it can completely destroy the ability to represent kind of language that was already trained. So for evaluation, we tried to estimate the fertility of these vocabularies and the vocabulary size itself. For model, we tried to estimate the next token prediction accuracy and non-existent word ratio. Here is the representation of this model. So we have 4 versions of BPE with the 3, 5, 10, and 15,000 vocabulary size, and also the 3 versions of vocabularies that was created. And unfortunately, as we can see as well, that the length was not reduced in comparison to the standard BPE implementations. Here is a more, I guess, objective representation. So we take the data set of UberText and try to represent them. And as well, we can see that BPE actually performs better in case of the representation in comparison to vocabularies. And it can be explained by the fact that actually BPE extract all these parts from the text itself. And as our vocabularies are outdated and they might not represent the words from for example, the law or with the news, or they might not represent some neologism. That is why they might not be the best solution for this kind of representation. Finally, with the model, we tried to actually train and compare two GPT models. Unfortunately, we could not reach the representable generation for this model, so we could not compare the performance on for these two approaches. So in conclusion, we created the first version of the morpheme vocabulary that can be developed. We proposed an approach of applying it into language representation and into the training pipeline. And I guess we highlight the major problems is the lack of the morpheme source and the distribution mismatch between the text and the vocabularies. So limitations is lack of convergency, sources of morphemes that are outdated and might not be enough to represent the language. For future work, we suggest to create new versions of the vocabularies with the mining new data sets, or maybe engaging some experts in the linguistics to make them better. Also, we have a problem of representation of apostrophes. So as they are represented in these old versions of vocabularies, there is an uncertainty how to represent them better. So maybe it's worth to validate this as well. And it would be good to have some metrics for tokenization effectiveness. So we want to combine two metrics, is the vocabulary size and the number of words unique that this vocabulary can actually represent. And we have one more application, is a byte latent transformer that was released by Meta. So it actually eliminates the necessity of having all these explicit tokenizers. So maybe it would be better to use them. It also needs to be validated. That's it. So here's the acknowledgements for people that was supporting this research. Of course, the advisor of this work. Also, I want to say thank you to the Department of Applied Linguistics for sharing this their database of morphemes for this research. And that's it from my side. I'm pretty sure you have questions, and I'll try to answer them.
Who would like to start?
Загроза Вадиму давати мікрофон. Yes, I do. Thank you, Vitaly, for your presentation. Obviously, tokenization problem is a huge issue for creating Ukrainian LLM. And seems that your research is quite a good example of the research with negative results. So far, I want to start with the question, how do you state your research hypothesis? So because you validate some, so you state hypothesis, and then you validate it and received SVC kind of negative results. So can you formulate those hypotheses?
Yeah, so the hypothesis was that to actually estimate that is it possible to kind of apply the transfer, some kind of transfer learning from humans of this language representation on the models. So as we can see from these versions of vocabularies, it didn't work. It does not mean that the application of morpheme itself is not applicable to Ukrainian language at all. It requires additional research, maybe creating new versions of these vocabularies, or at least to maybe focus on some pre-selected corpus of texts and applying this morpheme splits on this. So actually, we can try to set up the experiment is when we choose some predefined corpus of texts, we ask the expert on this field to actually map this text into the tokens, into the morphemes. And when we have this representation, we can try to compare it with something that was produced by PPE. And then we can, based on this, when we have this kind of more strict conditions, then we can compare them, I guess, in a more objective frame.
Okay, I want to jump to BP. So I'm not quite sure about what did you do with BP in your research. So have you recreated with this Ukrainian data set? So it was completely another approach from your side.
So what we try to understand is that BPE with having enough context and enough corpuses of text, it theoretically can represent the splits that actually used in morphology. But for that, we required huge corpuses of text, and we don't have it for now. So it was just a comparison to see what actually BPE showed us. It was used that we defined the alphabet, so Ukrainian alphabet. Starting from that, we applied the BPE and tried to actually fit them to different sizes. So that is why we had 4 versions of them. And we tried to see which tokens it could extract from there. And then we wanted to compare it with what actually the morphology of Ukrainian language can propose us with this text.
So to conclude, as far as I understand, BP is more implicit approach. So we feed the huge size of data, and then somehow we get this tokenizer at the very end. But your approach was more explicit. You provide this morphological vocabularies and try to compare this explicit tokenizer created based on the data set.
Yes, so actually what BPE do, it tries to extract these generalities from the text that was given to the input and then applied it for the generation. What we try to do is actually to try to, let's create some general vocabulary that in perfect scenario can cover all these combinations of Ukrainian usage and try to go from general to some particular cases. Because for now, when we use BPE,
and this, excuse me, and this general vocabulary you're talking about is
actually what we try to find. So some knowledges from linguistics. So
so you mean the vocabularies you used from those our data sources?
Yeah,
you're talking about the same vocabulary.
Yeah.
Okay. And my last question is about this final validation on GPT-2. As that you didn't get good results. Your reviewer stated that it's the main drawback of your research, and but after submitting your thesis for reviewing process, you had a couple of weeks, as far as I understand. Have you tried to think or evaluate what was the reason of failing with this GPT-2 evaluation?
Yes, so after that, we had a few more session of trying to rerun this problem. So it's one of the assumption why it actually works bad. So the first assumption was that the Uber text that was used for this training was not enough for covering our necessities. And the second reason, I guess, it was the lack of technical understanding of the training process and how to set up it correctly, as reaching convergency is requires some deep understanding of this tuning to actually reach the model that can show good results. And I guess that is the lack of this, maybe even experience in the training.
Okay, thank you.
Could you please go back to slide number 3? Well, you mentioned that TF-EDF is used to represent a text in a numerical format. I wonder how would TF-IDF as a metric could be used to represent a text in a numerical format. Could you please elaborate on that?
Yeah, so previously with NLP task, when we, for example, do the classification, we're trying to actually find the keywords that indicates to which could indicate to our target task. For example, we do the classification. When we process the corpuses of text, we're trying to understand which words or which part of text are very common, which is not. And then using this frequency representation, we can actually filter out the some part of the words that are most common, and they we can find them in any text, and they actually as not good indicators to what we want to find. And then we can use these frequencies as as numerical representation for as an input to, for example, the neural networks.
For what? Classifying, for clustering, for doing what?
Yeah, for example, for classifying. So it's just a way to represent text information into the numerical format.
No, I am a little bit afraid that this would not be a text representation because it's irrevertible. You cannot go back from this numerical representation to the text.
Oh, okay, I got it. It's not directly applicable, for example, for large language models, but for example, for the application when we actually don't need to get back to text representation, it could be applicable. So in case of the classification, for example, in systems that, I don't know, for example, for filtering, it can be applied.
Okay, just not to take a lot of time, slide number 5, please. Here you mentioned semantic structure. What do you mean by semantic structure?
So the one letter itself does not actually give us a lot of information. What part of it is it? And even bigrams, when we have the combination of two letters, we still cannot, with these two letters, we cannot deliver any sense. So
but this is about semantics, not about semantic structure. What is semantic structure? Which is the structure of semantics in my representation, in my interpretation. Is it so?
I'm not sure I understand.
Okay, let's go to the next question. How would you assess the completeness of your morpheme vocabularies?
Yeah, that's actually...
It's not about them being outdated. It's about their completeness.
Yeah. So that's the part of it I mentioned in the future works. So we don't have, for now, the way to validate them. In perfect scenario is something like when we have the vocabularies of all possible words and forms of Ukrainian language. And using it, we can estimate how completely the morpheme vocabularies can cover the Ukrainian language. Unfortunately, I guess this morphemes vocabularies is the best that exists so far.
So you didn't try to assess the completeness even indirectly by applying this morpheme dictionary as a part of a tokenizer to an available Ukrainian dataset?
Can you repeat the question, please?
A way to indirectly assess the completeness of your vocabulary would be to apply it in a tokenizer to a publicly available Ukrainian dataset, Uber, for instance, Uber text, which you mentioned. Did you try this to assess the completeness?
Actually, not. It wasn't measured, but I guess as a solution for that, yeah, it would be reasonable to filter out the words from input corpuses of available text in Ukrainian, and to see the difference between them and estimate it, and maybe to process them additionally.
That's what I'm saying, yeah.
Yeah.
Did you contribute a tokenizer as a result?
Yeah, we discussed it, how to share actually the current state with the open source for other researchers. Maybe it will be useful for them. So as for now, all these resources that was used, we need to understand how to do this from the perspective of licensing, as we did not reach the authors and ask the permission for that. It was used just for this exact experiments. So for now, we are trying to understand how we can share it with people who might be interested with them. Yeah.
So did I understand it correctly that you used an off-the-shelf tokenizer? Or you developed a tokenizer yourself within this project?
We developed the tokenizer based on the vocabularies, yes.
And the vocabularies were never licensed inappropriately, yeah? Okay, thank you. I'm done.
I would like to hear a little bit more on this. So you mentioned a database, and you also mentioned that database that was shared with you. You also mentioned that you applied OCR. So I don't understand. This database is already consists of morphemes parsed.
Yes.
So and then is this a scanned version or something like that? Why I don't understand. Why did you apply OCR if you already have the database?
No, database is something that appeared later. So firstly, we have only the first two resources, and we need to somehow work with them. Also, these sources might not be intersected. So for example, they can represent the different distributions. So the database is actually the only one that was in a digital format. The remaining are just printed actually books.
Okay, so have you somewhere published your results on that you applied the OCR, and as far as I understand, you extracted morphemes too. Have you somewhere published that?
We want to publish it for the Lang UK community for further researchers, yeah. But also this database is private, so we cannot share it at all. Only after some communication with this.
Okay, I understand. So you have your version. Have you tried to apply your algorithm on your version of morphemes that could be potentially publicly available?
No, but these versions of the morphemes was extracted from the printed books.
Yes.
And they cannot be shared directly.
Interesting. Okay.
Thank you for your presentation. I was surprised that you compared Ukrainian to Turkish, but didn't mention any Slavic language as a base of comparison, like Polish or Slovenian or Slovak.
It was an example more to show the difference of how languages is constructed from different parts. So it's not like the segmenting the languages together. It's more like to highlight the contrast, how they actually constructed.
But did you investigate how this problem is tackled with in Polish, Slovak, for instance, languages? Because there certainly are also very active communities very researching NLP. Why not mentioning?
Yeah, to be honest, during the research, we didn't see any research that was published regarding the Polish, for example. Yeah, I did hear that they developed their national language models, but during the research, unfortunately, I couldn't find any in the resources that can be.
And also about the ultimate goal of the research, you certainly want to develop an optimal tokenizer. But what is optimality? It's not the ultimate goal to make a tokenizer that is, for instance, has the best fertility. Fertility is not a direct indicator of how good this tokenizer is, because for German, for instance, certainly one word can represent one combined word can represent some very complicated notion. Yeah. So the number of tokens per word is probably not the only indicator of how good the tokenizer is. You have to understand how your tokenizers helps LLMs to handle the language and perform some specific tasks. And I didn't hear, probably I missed, but I didn't see anything of that analysis.
Yeah, that is why the idea was to actually try to estimate the fertility rate in combination of the comparison performance of GPT-2. So this analysis was not completed, obviously, but yes, in general, we need to actually take into consideration the vocabulary size which this tokenizer produce. We need to take into consideration the fertility rate, and of course, we need to having all this numerical comparison, we need to as well compare how these language models actually generate the language. And these three metrics might be compared in complex. Yes.
Okay, thank you, Vitaly. Student is Maxim Palamaryuk. He was advised by Igor Babin, and he will be presenting the work entitled Multi-Object, Multi-Attribute Text-to-Image Generation, Enhancing Semantic Alignment.
You hear me well?
Yes.
All right.
Take your time.
Good morning, dear audience. My name is Maxim Palamaryuk. I'm happy to present my master thesis in topic multi-object and multi-attribute text image generation. The work was supervised by Igor Babin, machine learning team lead in Advasoft. Today's presentation will take us from introduction motivation to experiments, results, and future work. Step by step, I'll explain the key ideas behind this research. Text image generation is a task of translating natural language prompts into corresponding visual representations. It connects NLP and CV, enabling models to create visual content based on human language. And nowadays, text image diffusion models can produce impressive visuals, but once you push them with multi-object prompts, they start to break. Considering some prompts like a dog, a frog, and a cat on a beach, it seems simple, but current model often mix up attributes, forget about some objects, or blur up special relationship entirely. And this is not just a quality issue. This is a fundamental semantic control problem in attention layers. This model does not truly understand the structure of the prompt, and that's why the research matters here. Because if we want this model to scale into design tools, educational content, etc., they need to be more controllable in providing semantic alignment between prompt and images. To understand the source of these challenges, we need to look at how the model is built. The architecture you see here is a simplified pipeline of stable diffusion. First, the text prompt goes into a pre-trained text encoder, often CLIP, which uses attention to transform words into a group of embeddings which store semantic information. Next, these embeddings guide the UNet denoising network through cross-attention layers. At each step, UNet refines random noise into a structured latent representation, and finally, a decoder converts this latent space into a high-resolution pixel image. These architectures allow efficient and high-quality image generation, but as we will see, attention layers are also where things start to break down when multiple objects and attributes are involved. Stable diffusion uses a CLIP encoder which applies masked causal self-attention. This means that each token attends only to the token that came before it. So this approach introduces a left-to-right semantic bias. For example, in the prompt like a cat and a dog, later token dog will carry residual information from earlier token cat. And as a result, their embeddings become entangled. This is the first place where semantic leakage appears when the model starts to lose clear distinction between objects even before generation starts. Now let's look at what happened during the denoising in the UNet. Here, cross-attention layers are responsible for grounding each text token into a specific image region. As the denoising progresses, this maps becomes more sharper, meaning that model becomes more confident about where to place specific objects. But when multiple tokens like cat and dog compete for the same region, their map starts to overlap, leading to object fusion or attribute mixing. In addition to cross-attention, the UNets also use self-attention on image features. This allows the model to capture long-range dependencies and connect image regions that share similar patterns or textures. But it has a drawback, because when the scene includes a semantically similar object, in this case like giraffe and zebra, their image feature may activate similar responses in both cross-attention and self-attention layers. This shared activation can blur the boundary between objects, making it harder for a model to distinguish them clearly. In multi-object text-to-image generation, we typically see three major types of failures. The first one is catastrophic neglect. This happens when object or attribute clearly mentioned in the prompt does not appear on the generated image. Also, incorrect attribute binding. This occurs when attributes meant for one object is mistakenly applied to another one. Also, subject fusion. In this case, feature of one subject visually merges into another one. All these failures appear because of confusion, or as it named in related works, leakage in attention mechanism. And this is the main issue we are mitigating in this research. Existing methods propose different techniques created to improve multi-object generation. One of the most well-known is Attend and Excite, which introduced a concept of generative semantic nursing. The idea of this concept is to optimize the latent noise during the noising, so that each token activates, each token attention activates a distinct spatial region in the image. This is done by applying a loss function on cross-attention maps, and the model is guided to increase attention for every subject token. This is very effective in fixing catastrophic neglect, but the method does not address attribute binding and subject fusion, because it does not explicitly prevent the overlap of attention regions. Layout to image methods, such as Be Yourself framework, usually also modify latent code or cross-attention map during the noising, but they do it in a bit different way. They work by adding strict spatial constraint during generation. User provides bounding boxes for each object in the scene, and the model applies a loss function that forces the attention map to stay inside this bounding box. In Be Yourself, constraints are applied to both cross-attention maps and self-attention regions. In cross-attention, they restrict the attention to be only in this specified region, but in self-attention maps, they also take background into account to maintain the spatial coherence. This, of course, improves the control over object placement, but it relies on user input, which limits its flexibility in real-world applications. And also, there are embedding modification methods which intervene early in the pipeline by improving text embedding. This helps to reduce the semantic leakage even before the generation starts. And token merging methods, it groups tokens in a way that maintain object attribute association while keeping the while reducing entanglement in the embedding space. It helps to improve attribute binding, especially when prompts contain very semantically similar objects. However, the methods produce the merged representation, which can sometimes be unusual, which leads to out-of-distribution results. In summary, each method targets only part of the problem. Some target and improve the text embeddings, other refine attention during the noise, and additionally, some methods heavily rely on external inputs such as bounding boxes and segmentation maps, which makes them harder to use in open-ended scenarios. But to comprehensively mitigate this problem, we should address both sources of semantic leakage, both text encoder bias and attention leakage in the UNet. To address these challenges we have discussed, we propose inference-only multi-stage framework based on latent diffusion models, which use cross-attention for text conditioning. Our framework combines 3 stages: embedding post-processing, attention refinement, and explicit object attribute binding using cross-attention alignment. Each part is designed to target a different point of the model where semantic leakage can appear. The first stage of framework is embedding modification. The main goal here is to reduce information bias introduced by text encoder in the generated embeddings. And to do that, we not only encode the full prompt, but also encode key object tokens in isolation. For example, in the prompt, a green apple and a red train, we separately encode just word apple and just word train. And then we apply gradient-based optimization with 2 objectives. The first one is to increase similarity between each object token from the base prompt and its isolated version. And also we are trying to reduce the similarity between embeddings in different objects so that apple and train are well separated. Unlike Tommy, which often produce out-of-distribution results, our method modifies only object-related token and leave the rest of the prompt embeddings unchanged. This gives us small but stable improvements while keeping original semantic at the prompt. But even with perfectly disentangled embeddings, object fusion can still happen because during generation because of overlapping attention maps. So the second stage of our framework is attention refinement, inspired by generative semantic nursing concept from attended excite. Here we optimize latent noise using two types of loss objectives. The first one is the intramap loss, when we maximize the total variation within each object attention map, which sharpens and concentrates its spatial activation. And also the second loss is intermap loss, where we are trying to maximize the Jensen-Shannon divergence between every pair of object attention maps. So that each object gets its own distinct region as the image. And together these objectives ensure that attention maps are both sharp and non-overlapping, giving us more precise control on where each object will be placed. And final step of our pipeline is explicit attention-based attribute binding. At this stage, we directly copy the attention map of each object token to its associated attribute tokens. It guarantees that perfect spatial alignment between each object and its attribute. It also reduces artifacts from generated image, as you can see, and it does not require any additional gradient steps. So each stage in our pipeline works at inference time. We modify only text embeddings and latent noise without changing in model weights or needing any external supervision. To evaluate our framework, we use the T2I ComBench, a benchmark specifically designed for compositional text image generation. It contains over 8,000 prompts categorized into attribute binding, object-to-object relationship, numeracy, and complex in composition. Also, this benchmark proposed different evaluation metric for different categories. To evaluate attribute binding, we use a disentangled version of BLEEP vision language question answering. We break the prompt into object attribute pairs, and for example, from the prompt a blue backpack and a red bench, we generate two questions. Is there a blue backpack, and is there a red bench? And the model is queried with these questions and generated image and if it responds yes with high confidence, it means that the attribute was correctly rendered on the correct object. For evaluating 2D and 3D spatial relationship, we use a UniDet for object detection and also depth estimation model for 3D spatial analysis. After detecting the object, we compare their position according to the spatial relation word from the prompt, for example, left to or in front of. And so then we compute the spatial score based on whether the actual position match what is expected. And to evaluate numeracy, we extract the number of objects from the prompt and compare it with what is actually generated. Again, we use UniDet for object detection. And also for complex and non-spatial relationship, like a dog and a cat playing with a ball, we use clip score. This metric is based on a clip model, which embeds both text prompt and generated image into the same latent space, and then computes the cosine similarity between these embeddings. A higher score indicates better alignment between the image and the prompt in a semantic sense. Now let's talk about results. We evaluated our framework against Stable Diffusion 1.5 and 3 other approaches. We did a separate evaluation for different prompt categories from the benchmark. On the table, you see evaluation for attribute binding category with color, shape, and texture subcategories. We achieve 25% increase in average compared to SD 1.5 baseline, and several percent improvements compared to other methods. The most significant improvement is in color binding, which is about 35% compared to SD 1.5. In shape binding, we achieved 16%, just behind token merging technique, which is specifically designed for it. And in texture, it's again 25%, overperforming all the other methods. On the image, you can see qualitative results for color binding category and also scores for all of them. Yeah, you can see that we not just managed to produce correct colors, but also consistently generate both objects in the scene, and the presence of two requested objects improve performance across multiple metrics. However, in the first example, you can see that the generated objects appear somewhat unnatural, which is slightly affects spatial coherence visually, and I'll talk about this a bit later. Here is our result for shape binding. You can see that we managed to generate semantically accurate shapes, reducing catastrophic neglect, of course, and object fusion, and also keep the correct attribute. But still, in the second image, you can spot a few artifacts. For example, a small golf balls close to like a main one, which show that there is a room for improvements in precision. The text binding task is very similar to color binding, so I won't go into details. But compared to attend and excite and divide and bind, our method produced fewer artifacts, such as extra or misplaced objects, and provides a clear improvement over Stable Diffusion 1.5 baseline. Here are results for spatial and numeracy categories. Only in numeracy category, our pipeline score is slightly lower than attending site, but just by 0.04%. But it's important to know that our pipeline was not explicitly designed to improve spatial relationship and numeracy. These gains mainly result from better semantic alignment in multi-object prompts, because we managed to generate several objects on the same image. Here you can see qualitative results for this subcategory for 2D spatial. You can see that for the first prompt, our method generates pretty much the same results as like two other methods. It means that in this case, the generation is was done on the several changes in the latent noise, because it was pretty much aligned. And also the second image, you see like all the methods produce not very good results because, as I said, spatial alignment was not targeted. Again, you can see here clearly improvements in semantic alignment, because our pipeline managed to generate the images without with distantly two objects and without a lot of artifacts such this the other methods. In numeracy, you can see that there are no major improvements from Stable Diffusion baseline. Also, we see improvement in non-spatial and complex prompts. The performance is clearly better than both baseline and most competent methods, and this shows that our framework scales well to harder real world prompts because of this multi-stage approach that targets both embeddings and attention during the unit denoising. In this example, you can observe strong correspondence between prompts and images. Actually, in most of them, in most of methods, there are clear improvements compared to Stable Diffusion 1.5, and also at this image, you can see that not only attributes are correctly placed, aligned with each object, but also there is a yellow grass as it was requested. But there are also some failure cases that I want to show you. Actually, we have identified 4 of them. The first one is compositional and perceptual failures, which you can see on the first image. Also, some object over representation appears sometimes. And of course, object ignorance in complex prompts, such as prompt with get. And as I said, unnatural placement of object in some prompts. Yeah, we can discuss it later. And as a limitation, we see that current pipeline does not explicitly optimize the spatial relationship and numeracy. Also, objects counting are not addressed. Yeah, and also the pipeline, our framework introduced additional inference time steps, increasing memory usage and computational cost. As a future work, we see that it makes sense to apply and benchmark our framework on newer architectures such as Stable Diffusion XL and Stable Diffusion 3. Optimize, of course, pipeline for real-time and low resource settings. There are room for optimization, and also to target spatial spatial consistency. We can use a spatial reasoning model to better align in 2D and 3D prompts. Last but not least, I want to express my deepest gratitude to my supervisor, Igor Babin, for constant support during this research, and Advasoft for providing me with necessary computational resources for my experiment. Actually, that's it. I thank you very much for your attention. Ready for your questions.
Would like to start?
Thank you very much for your very interesting presentation. You have ablation study in your thesis, but you didn't.
Yeah, I have it here on the slide.
Okay.
Yeah, I didn't mention it in the main presentation because I knew that
as I know,
somebody will
ablation
ask.
study, it's very important part of work if you introduce something new. So it's important. But my question was, is you don't train the model. You just use model in inference regime and add some 3 like post-processing steps. And when we in machine learning in general, we deal with trade-off. So sometimes when we improve something, in other side we can have drawback. Could it be your approach reduce number of artifacts, right?
Not only. The approach is first of all targeted the multi-object generation to generate 2 objects, because if you want for example, Stable Diffusion 1.5 to generate cat and dog, it usually provides 2 cats. So we target it, but also as a side effect, we reduce some artifacts from the generation, especially compared to other methods such as divide and binds and attend and excite, which was mentioned before.
But my question is, could it reduce to, could it lead to reducing of variability of the generated images? In generated models, it's very important.
Yeah, okay, it's a nice question. Actually, we do this optimization of latent noise during generation, but only for the half of steps. So we make this optimization at the beginning, and then the model continues to generate as it was before, without big changes in the latent representation. So at the beginning, we target like the spatial placement of the object, but the later steps improves the high-level details, and also, yeah, when we don't have artifacts, it does not make these artifacts bigger.
Thank you very much. Very impressive work. And don't forget about the ablation study.
Sure, thank you.
So I'm also curious, you mentioned about this trade-off that it introduces additional computational overhead. Have you maybe measured and compared it?
Yeah. So as an overhead, we have like in runtime increase it's depending on the prompt and the start noise is from 40 to 300% per image on NVIDIA 1390. Because vanilla stable diffusion like generate the image for in 4 seconds, our pipeline from 6 to 16 seconds. Yeah, with 50 steps. Also, it consumes up to like twice more GPU memory, but it just because of attention maps that we store to visualize like for this presentation and for thesis. So yeah.
And a bit a tricky question. How did you choose images or examples for the presentation? Was they randomly sampled from the result or carefully chosen?
No, actually, it was a random choice. I know that in research, usually the results are cherry-picked. I did the evaluation for all these methods, and I just chose the random images to see it. So it was not carefully chosen. It was a random one. But when I saw that, of course, I have a lot of like this qualitative results, and I tried to choose such stable diffusion images in which images from base model where we clearly see the issues which were targeted by my methods and all other methods.
And also, you mentioned that you kind of add extra tokens for the objects. How do you know what is the object? How do you?
Actually, for this, we have a small model that like there are two ways. For my experiments, I just chose tokens like manually, but to do the whole evaluation for 8,000 images, we have a small model that's named entity recognition model that take objects and attributes from this prompt.
I see. Thank you.
I have a question. As far as I know, like this model, very sensitive from hyperparameters. Do you research this problem in your work?
So yeah, as I said, we built a framework that's just on top of the baseline model. So we do not change any hyperparameters. They work as before, like for Stable Diffusion 1.5. Of course, our framework introduces its own hyperparameters. For example, we can set up like how many steps, like this optimization steps will be done for embeddings during the denoising separately. Also, we have some thresholds for these optimizations. So we were like playing with hyperparameters of our framework, but we didn't target and change hyperparameters of like the baseline model, because we the idea of this framework is just to be on top of it, not change it somehow.
Thank you for presentation. I have a bunch of questions, I think, in continuation to the previous question regarding your evaluation approach. So first of all, can you just go back to like to your evaluation framework slide? Like my question, did you try to compute like some classical metrics for generative models like fit or something like that, just to make sure that while you solve these problems, you do not degrade in again in the generation quality and generation reliability?
Okay, thank you. Actually, I didn't try FID metric for this. This is mainly because I did a lot of experiments with images. I saw a lot of images during this generation, and yeah, I just understand that most likely it doesn't make sense to do it, because I didn't see the like degradation like in the generated images. Yeah. Also, FID just measure how well the generated image like compared to the statistical distribution of all the images. So as I said, we like on the last 25, for example, in this case, we run only 50 steps. On the last 25 steps, the stable diffusion works without any optimization. So it like we just target the correct placement of objects, and then stable diffusion like does all the other work. So it does not like almost doesn't change the structure, sorry, the visual representation of the image.
I see. But yeah, overall it will be,
Yeah,
I think, interesting
agree.
just to be sure that. Okay, and regarding another question, like as we deal with generative models, as I understand you need to run like several generations in order to compute like statistical significant metrics. Have you observed like some confidence intervals and like overall statistical significance of your results?
Yeah, so for this, we did run this 8,000 prompts several times for different seeds. And like this is just the average results based on all of them. So I didn't compute the statistical structure of this, but yeah, I did it not only in one seed, but at several ones. So like generating it was more than 30,000 images for one model.
Okay, I see. And I think the last question, so you have, for one of the metrics, you have mentioned that you have used CLIP.
Yep.
And as I understand, it's the, as you have mentioned, like previously for conditioning, you also use CLIP. I'm just wondering whether like this metrics is not also affected by the problems that you have mentioned in your work, that that the CLIP model concentrates more on the last part of the prompt. So like your metric is also kind of affected by the same problem.
Yeah, of course, CLIP has its own bias. I will get back to here. Yeah, it has its own bias, but this is the metric that at least somehow can check the non-spatial relationship, and we cannot really measure something from prompt and so from generated image, because there are a huge bunch of possible generations based on one prompt. So CLIP is just, of course, it has its own trade-off, but it was proposed by the benchmark. So yeah, that's why we use it here.
Maybe just like an idea that you have like in your work, you have proposed like these modifications to the conditioning to the for the text. So maybe it will be interesting also to try this modification for metric computation, and it can also kind of give more robust results, like more representative results for multi-object.
Yeah, I think it makes sense. Yeah, thank you.
Thank you.
Okay, thank you.
Thank you very much.
So we have 1 hour break, and we will continue our defense session.
Active value alignment task is actually a classification task. And here we evaluate the specific choice of the LLM and use standard classification metrics like precision recall and F1 score. And the third task is passive value alignment, which is basically prompt injection, and it involves generating prompts that aim to elicit harmful content generation from LLMs. Here we used approach called LLM as a judge with a more advanced proprietary GPT-4o model, and we also use here human evaluation for GPT-4o model itself to avoid self-assessment bias.
Let's proceed to benchmark development. Our methodology consists of several consecutive steps. The first one, we need to select the domain for alignment evaluation. Then we need to select corresponding datasets from this domain, and then apply some rules and preprocessing for selecting a subset. And the last step is adaptation pipeline, which includes machine translation and linguistic refinements. So as for the domain, we selected ethics domain based on two main criteria. The first one is relatively short text here that enables efficient translation and experiments execution. And the second key point here is the challenging nature, because it requires LLMs to understand social norms and moral principles. As for datasets, we selected ethics and social chemistry 101 because they have exhaustive sampling, and also they underwent rigorous human evaluation to ensure data quality. So here is a key overview of key points from ethic dataset. It contains over 130,000 examples and was designed to preserve most unambiguous ethical scenarios. It covers 5 distinct ethical domains, and each sample is labeled as morally acceptable or morally unacceptable. The filtration process here included the selection of common sense domain, and the reason for that was that these common sense samples were generalized ethical scenarios, and it was only the only one domain that had underwent cross-culture evaluation and received a high inter-annotator agreement. The test set here contains almost 4,000 scenarios with varying lengths, and we selected 1,700 scenarios of the shorter text length, and this resulted in almost equitable distribution by labels. Moving on to social chemistry 101, here we have more than 100,000 real-life scenarios, mostly scrapped from the internet. And this dataset is structured around the concept called rule of thumb, which is the ethical judgment in natural language. And it has almost 300,000 of these annotations. Also, it is categorized into 5 moral foundations. While the dataset contains a lot of columns derived from the annotations, the key interest for us has the 2 of them. The first one is action moral judgment, which is conversion from natural language rule of thumb to the numerical scale. And the second one is rule of thumb agreement. This is an inner annotator agreement score. Here we selected the samples with the highest inner annotator agreement score. We also selected one moral foundation called care harm, applied the duplication, and mapped a 5-point scale to 3-point scale for simplicity. And it resulted in 3,682 samples with a relatively balanced class distribution. The next step in our pipeline was the machine translation. Our initial choice here was the Dragoman, as it has a SOTA performance on Flores 101 English-Ukrainian dev test subset. But upon our evaluation, we found it insufficient, and it did not manage to preserve the meaning of the actions correctly. So we proceeded to DeepL, LLM-based machine translation service that has become the most popular service in 2024. And while it performed much better, we still saw there a room for improvement. So we decided to analyze another LLM-based approaches, and we selected Claude 3.7 as the most prominent competitor to the DeepL. To make our final choice, we conducted internal human assessment of the translation quality by selecting 100 subsamples from each benchmark subset and annotating the preference. And as you can see on the chart, the Claude 3.7 preserves better translation quality, so we proceeded with it. We also wanted to ensure that the translation quality obtained was best possible, so we decided to utilize a SPIP-Outer model for some linguistic refinements. This model was trained on 4 objectives: paraphrasing, text simplification, coherence improvements, and grammatical error corrections. We tested 3 of them, and upon our review, we found out that paraphrasing can introduce new errors or add additional words that will change the meaning of the sentence. Coherence improvements can also add additional words, but GEC either preserves the text unchanged or fix grammatical errors. So we proceeded only with GEC. We also analyzed these improvements and categorized them by as unchanged, first letter capitalization and imputation adjustments, and sentence structure changes. 92% of all samples remained unchanged, which meant that clause 3.7 has pretty good understanding of Ukrainian grammar. Proceeding to our experiments, here we have a simple workflow with consecutive steps. First, we extract the sample from our data set, then inject it into the predefined prompt template designed for the specific task, then execute the target LLM, capture the output, and apply the needed output processing, for example, for extraction of classification label, then formalize the results and pass it to our evaluation framework. As for the model selection, in this work, we prioritized open source models with varying degree of Ukrainian language support to ensure transparency and reproducibility. Our final choice included AI models family, which has listed Ukrainian as one of their primary languages. And from there, we choose AI Expanse and AI 101. As for the general multilingual models, we choose Llama 3.2, Gemma 2, Qwen 2.5, and Gemma 3. We also included one proprietary model for comparison, choosing GPT-4o. The first set of experiments was executed on the subset from AI evaluation suite. And as I said before, we utilized 2 different BERT-based models for this purpose. And we observed that the results vary significantly by model. And upon our further analysis, we also identified that high scores were assigned even when the generated text missed some crucial content from the reference text. While the evaluation approach here could be improved because of the quality of the data set itself, which was translated via Google Translation a few years back, we decided to focus more on our benchmark development and performing experiments with it. So here is the experiment results of our developed benchmark. This is ethics subset, and GPT-4o has the best score here. And but among open source models, Gemma 2 has the closest score to it. Also, almost all models produced better results on English than on Ukrainian, with the exception of AI 101. And Llama 3.2 had the biggest gap between the Ukrainian and English performance. As for the social chemistry 101, the difference between the language evaluation results was not that significant. And here, even several models exhibited better performance on the Ukrainian rather than on English. And surprisingly, here the Gemma 2 outperforms the GPT-4o. But again, Llama 3.2 and Qwen 2.7 have the biggest gap between Ukrainian and English results. We also observed several additional model behavior patterns. Llama 3.2 has some strict alignment around some topics, especially suicide-related, and refused to engage even for the classification tasks. You can see the distribution of these refusals by the subset and language on the right. And there are much more refusals for English than for Ukrainian. And also another observation was that Qwen 2.5 struggled with structure output and failed in generations in approximately 6.5%. Another separate topic of experiments was passive value alignment. As for this purpose, we constructed another subset. We took our developed benchmark. We extracted from their samples where Llama 3.2 refused to engage. We added also samples that contains yelling keyword. Then we filtered them by label to preserve only morally problematic scenarios. And after then, we conducted internal human evaluation of the translation quality to select only the best possible choices. And this process yielded with 82 samples of morally problematic scenarios. And we also designed a simple prompt that was encouraging the model to praise this bad behavior. Evaluation results here were quite surprising because models rarely refused to engage or defend some moral principles. The most consistent here was GPT-4o, but Llama 3.2 outperforms it on the English subset. And also an interesting observation is that Qwen 2.5 has much better performance on Ukrainian than on English. And the last observation here is that Gemma 3 has better performance on Ukrainian than its precedor Gemma 2, but on the English, the scores were a little bit lower. So in this work, we developed a new comprehensive benchmark for ethical alignment evaluation in parallel in English and Ukrainian. We also identify performance gap with Ukrainian notably performing quicker across most models. Also, we identified that open source models usually tend to underperform compared to the proprietary models. And IA models family, despite their primary focus on Ukrainian, did not outperform the general multilingual counterparts. And last but not least is that passive value alignment tests reveal some serial ethical alignment challenges. We also acknowledge the limitations of this work that can be categorized by benchmark design limitations and model selection limitations. As for the benchmark design, the first one, the most obvious one, is the translation quality. While we did our best to produce the most accurate results, it is still not comparable to the human translation. Another one is the culture scope limitation. While we also try to select the most unambiguous ethical scenarios with high inner annotator agreement, they still may not reflect the Ukrainian culture scope. And the representation constraint, as we selected only a small subset, a small subdomain from ethical scenarios. As for the model selection limitations, we assessed here on the only limited number of models. And another problem is that due to the computational constraints, we utilized model in their smaller variants. And thus we possibly limited some insights on the parameter scaling effect on alignment evaluation performance. So the future work is first to present the developed benchmark on the UNLP, and then the top priority is to address the benchmark limitation by collaborating with experts to improve translation quality. Also attract annotators to relabel the dataset to represent better Ukrainian culture scope. The next point is to expand the evaluation resources in Ukrainian to cover additional dimensions of value alignment. Also, as well, address a model selection limitation, assess a wider range of models, and investigate the impact of parameter scaling effect. And last but not least is to develop a specialized training data set and implement alignment tuning for the Ukrainian language. As for the reviewer comments, the reviewer had one major concern about machine translation introducing new bias, but in our thesis we selected the samples selected in our thesis were mostly pretty straightforward, with maybe complex linguistic structures. So the major concern was about the translation quality and meaning and capturing the meaning rather than introducing new bias. Also, upon our evaluation of the translation quality, we did not encounter a new bias introduced. And here you can see several samples from translation from our dataset. Thank you for your time, and I will be happy to answer your questions.
Anybody would like to start?
Many thanks for your excellent presentation. I have a tricky question, which you partially answered, but I would like to ask you to elaborate a little bit more. It's in the cross-cultural aspect. So you first mentioned it in your slide number 19. Could you please revert it back? So did I understand it correctly that you just removed the items which were culture specific from the English data set before trying to somehow transform it to Ukrainian, or?
Not exactly like this. Like this ASIC domains, it has 5 domains of ASICs in itself, and the common sense domain was underwent cross-culture evaluation. So we preserved
just common sense.
Yeah, and we took only this one because of that.
Okay. The problem is that something that is unethical in North America could be considered quite ethical in Ukraine and vice versa.
Yeah.
You mentioned also that you are in your slide number 31. 31. That the number of refusals is different for Ukrainian and English. Is it somehow related to this cross-cultural thing?
Not really.
Did you analyze it in a finer grain?
It is mostly related to the performance of Llama 3.2 itself on English and on Ukrainian. So we had the biggest gap between English and Ukrainian on Llama 3.2. So it's not that aligned on Ukrainian as it is for English.
So, and finally, the third part of the question: how exactly are you going to address this issue in your future work?
The cross-culture?
Cross-cultural, yeah.
Yeah, so the first step here, as I outlined in future works, so is to, after enhancing translating quality, we would like to attract annotators to relabel the data set, and then we can analyze the agreement rate between the existing labels and the new labels. And if they are very low, we can also seek for other sources and either crowdsourced or scribed from internet. And then once again, attract annotators to relabel them. So to have the representation of Ukrainian culture scope.
Also partially agree with the reviewer who mentioned that machine translation could introduce something. I do not really agree that it could be an additional bias. It could be an additional view on a pragmatics and cross-culture. Do you plan to do something in this direction to improve machine translation using your benchmark?
For this part, this is a silver benchmark. So
yeah,
the first step here in addressing benchmark limitation is to collaborate with experts to review this translation and improve it. So we will have like the golden standard.
So you're not explicitly addressing the machine translation stuff.
I do believe that
the downstream for your work.
Mm-hmm. I just do believe that we can there are two choices: either to address the machine translation bias and machine translation error, or attract the collaborators, attract the experts. So I do believe that inviting experts would have better effect on the quality of the data set.
Or you address both aspects and make it, well, super additive.
Yeah, I did that.
Thank you.
Thank you.
Thank you, Anдріан, for your nice presentation. I remember your talk at the PhD Master Symposium. Do you remember my question?
Yes.
Yeah. So does it mean that you didn't do anything in that direction? I mean, it's your future work to curate the quality of the translation, and therefore the results you presented today are not reliable.
Actually, we did these improvements with assessment of translation quality and introducing Claude 3.7 instead of DeepL based on the comments. So for now, we were focused on machine translation rather than attracting collaborators due to the limited amount of time. But yeah, we took into account these comments and we like selected better model for that. I actually have some translation comparison. You can, yeah. This one is a comparison between DeepL and Claude 3.7.
Okay, thank you. So, do you have any estimate what fraction of a machine translated data set requires human?
Unfortunately not.
Okay, thank you.
Okay, I'm curious. So I understand kind of the data part, that in order to align, of course, we need the data. And what about alignment approaches? For example, I don't know, maybe there are some strategies for alignment, and you could elaborate a little bit on that.
Yeah, actually there is reinforcement learning with human feedback, and there is direct preference optimization, which I think in future would be our choice. It eliminates the need for training a separate reward model. So yeah, these are the main two approaches. And there are like different variants of these approaches too.
And I am also curious, so as far as I understand, there are a lot of pre-processing steps that you did. And have you open sourced your code? Is it possible to reproduce these results? And
yeah, actually it's in public GitHub repository, and it includes all the steps with all the pre-processing steps and documentation for that.
Okay, so I guess we still have them.
Let's imagine that you have not 2 language, but for example, 5 language. Which the first steps do you need to do that for start the parameter scaling analysis for 5 languages, for example?
I think the pipeline here would be the same as for the 2 languages. We need to run the experiments on the different variants of the same model and then investigate the difference in results, whether they improved with bigger variants or not.
You mentioned probably on the slide number 32 or 33 that you inject, yes, this one, action yelling. Also, how was you, how you did it, and can you elaborate on this?
Yeah, actually, so there was.
Can you give some example of the prompt or how?
Unfortunately, I do not have it like in the presentation. There was some really morally problematic scenarios with keyword yelling, but there was also like simpler one like yelling on the strangers, something like that. This was like the action that needs to be evaluated. And why I added that, because upon previous review, I saw this this word repeated in some samples, and I just wanted to extend this subset of morally problematic scenarios.
Only with this case, I mean, only with the yelling and
in this case, only with yelling, because the other samples, like upon my review, I did not see any other like keywords that were presented in different samples, so we can like systematically adjust this data set and extend it.
Am I correct to say that you used, as we talking about Ukrainian, so it was like krичати?
Yes.
And have you any different synonyms for this?
Yes, there were in Ukrainian, but in English datasets there was mostly yelling. But
Yeah, but in your case, as far as I understand, you have all this
I selected I was selecting the samples from the English subset.
Okay.
Yeah, and there are translations.
Okay, I see. And then translations. Okay,
Yeah.
thank you.
One more question. You based your solution based on English, but it would be some benefits if we use more close to Ukrainian language like Polish. You use translation because these two languages more close to each other.
Yeah, that would be nice, but the problem is about the existing data sets that needs to be adapted to the Ukrainian. And as I said in the literature review, that most of the data sets are English only, and there exists like Chinese only and several multilingual, but this multilingual may include like Spanish and German, something like that.
Yes, thank you.
Thank you.
Jan, can you please return to this slide number 40 with examples of translations?
Yes.
I read and I am at a loss how should I actually, what label should I put there, for instance, for the second one or for the third one? It's very context-dependent situation. So did I stole these delicious finger sandwiches and ate, or I was offered them? Or the first example is exactly totally irrelevant for our cultural context, because there is no such thing as senior hours in supermarkets. So what do you do with those? So
yes, thank you for your comment. Yeah, for now we were only like taking the labels as they were presented in the initial data sets. So like I think on the steps of relabeling the data, this will change.
But what was the label for the third sentence? Is it appropriate or not, or forbidden, or?
To be honest, I don't remember, but
I was also looking at the first example, and I was lost in translation. So, in fact, if you didn't show us the second and third column, I would be unqualified to translate it properly without any context. Yes, as for senior hours, there were senior hours introduced in Ukraine during COVID. Oh yeah, we were not that senior by that time. And so there is a contradiction which could not be resolved within this very small window. So it just says that I'm young. This is why I went during the senior hours, which is a contradictory statement. So it does not say somewhere beyond the window that very young people are also allowed to do that with the senior people.
Mm-hmm.
So this is why the mistakes in both translations.
Yeah.
So it's a bit tedious, and I mean the example is not very representative.
The whole data set contains such sentences. Yeah. Questionable what we are measuring.
I'm sorry both for detail and flow.
Okay, so I guess this is a pretty rare occasion that we have finished Q&A session on time. Yeah, thank you.
Thank you.
So let's move on, and the next presentation will be delivered by Andrei Such, who is supervised by Artur Kulian, and he will be presenting a work entitled OCR-free document understanding using vision language models. Andrei, please.
Thank you for the introduction. By the way, can you hear me? Okay, so thank you for the introduction. Thank you for having me here, and I want to express my appreciation to Artur Kiolian for his advice and assistance. So today, the plan of this presentation consists of several steps. So we will go through the introduction on motivation, hypothesis, research roadmap. Then we will briefly go through the theoretical background, related work, review the conducted experiments and results, make conclusions, have a short performance demonstration on fine-tuned model. And I will be ready to answer to your questions. Sorry, I have a trouble with my. Okay, so motivation. I found it difficult to decide what I want to do more, either computer vision or natural language processing. That's why I chosen vision language models as they combine elements of both. They open up a wide range of applicability, and as starting point, I focus on visual document understanding, VDO. It was a practical choice since data sets for visual document understanding can be synthesized using available text data, visual layouts, common document forms and styles. Another reason for this direction is the limited support of Ukrainian language in current VDO research. So we hope, with this work, we hope to bootstrap a VDO dataset, set up evaluation methods and fine-tuning strategies. So the hypothesis in this research, we are exploring a few core hypotheses around capabilities of OCR-free vision language models. We believe that OCR-free vision language models have a potential to outperform traditional OCR systems. We are interested in evaluating whether open source OCR-free models can deliver results that are similar or can compete with proprietary top 1-tier systems. We hypothesize that vision language models are not just good at extracting text, but can also accurately capture document structure, including reading order, tables, hierarchical layouts, and can act as effective classifiers for Ukrainian language documents. And finally, we expect VLMs to show the high level of robustness to real-world image quality issues. The research roadmap consists of 6 steps. So first step was setting up document generation framework. Second step, creating a data set, then setting up the benchmarking methodology, pre-trained model benchmarking, visual instruction tuning with subsequent benchmarking of the fine-tuned model, and summarization of the results. So moving to the theoretical background, vision language alignment has become increasingly feasible with the development of several key techniques and architectures, specifically adoption of transformer architecture to the vision, which resulted in vision transformer, VIT. And attention map in VIT spans the full image context, which makes it particularly suitable for tasks requiring global understanding. But originally, VIT encoder was trained on fixed resolution images ranging from 224 to 384 pixels, which limits performance on high resolution and text-dense documents. With recent studies like NaVIT and FlexiVIT, it was found that VIT architecture benefits significantly from high resolution training and inference, and this is crucial for OCR and document understanding. That's why this native resolution technique was adapted to VIT, which packs multiple varying size image patches into the single token sequence, similar to packing tokens in NLP. Another important advancement is actually positional embeddings. However, The recent alternative approach is the rotary positional embeddings, which encode relative positional information directly within attention mechanism by rotating query and key vectors. This makes attention inherently position aware without adding extra parameters. So altogether, all these techniques, they combine into what we call a vision language model. The vision encoder processes the image, text tokenizer encodes the text, and the cross-modal connector aligns both modalities before passing them to the autoregressive LLM. And it's crucial, the design of the connector is crucial, and in recent studies like LAVA, it was found that multi-layer perceptron performs much better than just a simple linear layer. About related work, there are actually 3 approaches that we were able to identify. And the first approach basically just implies extracting the text from the image and passing this extracted text to the large language model for post-processing. This method benefits from mature OCR tool, but struggles with noisy layout, visual structure, and multilingual content. The second approach is OCR to VLM. With this approach, we simultaneously pass OCR output and visual representation image to vision language model. The visual context helps the model better align with the layout, improving interpretation, and the third approach is OCR-free VLM itself. In our review of the field, we identified 6 pre-trained models that satisfy 2 key criteria: OCR capability. This includes either explicit training on document images or strong performance on OCR-centric benchmarks. And the second criteria is multilinguality. The model must support multiple languages, including underrepresented ones such as Ukrainian. So the proposed solution, we introduced the semi-synthetic dataset specifically designed to support research on Ukrainian language, visual document understanding. The documents are generated using RAG pipeline. We begin by retrieving text content from Ukrainian Wikipedia by article categories. This text is then processed by the LLM using structured prompt, which produces coherent sections, including paragraphs, tables, and charts. To introduce a structural variability, we incorporate HTML tables sampled from pub tables 1 million dataset, enriching the layout with more complex table structures. We also apply controlled visual degradation, such as Gaussian blur, sinusoidal warping, brightness, contrast shift, low intensity noise, to simulate common scanning artifacts and imperfections. Most generated documents fall within 150 to 400 words range, and peaking around from 200 to 250 words. As shown in the box plot, the median word count is fairly consistent across all 3 types. This suggests that our content generation process is balanced, and a small number of outliers exceeding 400 words exist, but such lengthy documents are rare. Every image is paired with a rich metadata, including document category, rendering style, element type, bounding boxes, reading order, which is crucial for layout-sensitive tasks. And our dataset is publicly available on Hugging Face. We evaluate models across 4 benchmarks: OCR benchmark, document classification based on its content, table structure extraction, which aims to recover the underlying layout of the table, outputting structured markup like HTML. And finally, document layout analysis measures how well model can identify and sequence structured elements in reading order. The metrics we use for the OCR are character error rate and word error rate. However, to align OCR metrics with other benchmarks where higher values indicate better performance, we instead report the complementary score, character correctness rate and word correctness rate. For classification, we use accuracy. For table extraction, we use tree-added distance similarity, and for document layout analysis, we use our custom metric, which is the cosine similarity of predicted versus ground truth reading sequences of document titles. We apply two distinct prompting strategies. The first strategy involves feeding the model with a complete document image alongside the task-specific layout, and the model must reason over the entire page layout and identify relevant content. The second strategy uses the grounded image regions where specific sections of the document, such as text blocks and tables, are extracted from individually paired with a corresponding prompt. So in this case, the model focuses not on the local content and of the cropped region of the document. Experiments and results. So basically on this slide, we present the benchmark results for all evaluated pre-trained models alongside the classical Tesseract OCR engine. Tesseract is a long-standing OCR system originally developed by Hewlett-Packard and later maintained by Google. As we can see, even the 4-bit quantized version of Qwen model outperforms Tesseract across all measured benchmarks. We also observe that Qwen performance improves further with full precision inference and with the newer model generations. So comparing the classical OCR versus open source models, however, we can see that not all models coped with designated tasks evenly well. Specifically, P multimodal and Aya Vision lagged behind in text transcription, but performed better on structure-sensitive tasks like table extraction and document layout analysis, when Qwen demonstrated the strong, consistent performance across all benchmarks. If we look to the top 3 models, among these, Mistral is different, as it follows the OCR to VLM integration, where both OCR output and visual input are passed together to the VLM. However, as we can see that extended setup does not appear to provide the considerable performance gains. In contrast, Qwen and Gemini delivered strong and more robust performance across the board, not just in OCR tasks, but also in table extraction, document layout analysis, and document classification. And it's also worth to mention that Qwen model competes head-to-head with Gemini, which is presumably a larger model than 7 billion for Qwen. We further explored whether the pre-trained Qwen model could be fine-tuned to surpass Gemini across all benchmarks by applying visual instruction tuning with PEFT and LoRa. We refer to the resulting fine-tuned model as Ukrainian document adapter. So LoRa adapters were integrated into both self-attention and MLP modules throughout the transformer encoder and decoder, resulting in 51 to 103 million trainable parameters. So to prepare the training and validation data, we applied a document inflation process to the original 1,000 documents. Each document was split into individual sections, which were added as the standalone training examples alongside the full document. They were paired with the corresponding text prompts and ground truth content, resulting in 7,200 image content pairs. All 3 LoRa configurations converge quickly, with training loss stabilizing within from 200 to 400 steps. Across all benchmarks, the fine-tuned model consistently improved the performance. For instance, OCR scores showed particularly strong gains at the document level, closely matching those at grounded text regions. And notably, for table extraction benchmarks, all three experiments document level tree edit distance similarity outperformed the those based on the ground tables. Sorry. Yeah, so this is just to emphasize that model can actually perform better when it's given the complete document rather than when it's given the cropped regions of the document. So among three configurations, the mid-size variant achieved the best overall performance. If we compare the fine-tuned versus pre-trained models, a direct comparison, basically our fine-tuned model, it outperforms the pre-trained models on almost all evaluation metrics. The only exception is word correctness rate on grounded text, where Gemini maintained the edge, likely due to Gemini's pre-training on short text segments. However, on document level OCR tasks, the fine-tuned model achieved 99 for character correctness rate and 97.6 for word correctness rate, far surpassing Gemini's 90.3 and 91.2%. Regarding the model robustness, handwritten font caused the most significant performance drop in OCR tasks, especially word correctness rate, affecting both Tesseract and pre-trained VLMs. However, handwritten documents do not handwritten documents do not hinder structural tasks like table extraction. In fact, they may even aid in structural recognition. Scanned documents performed almost as well as print style inputs across most tasks, suggesting that typical scanning artifacts have minimal negative impact. And after fine-tuning, our adapter shows strong improvements on handwriting and scanned documents, where it even outperforms print style inputs on some tasks, likely due to training augmentations that improved generalization. So to conclude, with this project, we believe we have proven our initial hypothesis. So to summarize, these results reassure that OCR-free VLMs are viable, scalable alternative for real-world multilingual document understanding. The future work includes expanding a dataset scale and diversity by incorporating more document classes, layouts, content styles, validating the results with a real-world human annotated dataset, to assess model generalization beyond the synthetic data, expand beyond VDO, and build custom VLM by combining pre-trained vision encoder and LLMs using trainable projection layer. And I prepared a small presentation to just at least slightly eliminate a bias that since model was evaluated and trained using semi-synthetic dataset, I just picked a few real-world documents, and I want to demonstrate how it performs. So I have a fine-tuned model running on GPU instance, so I can actually I can choose some document. In this case, I have a handwritten document of one of Ukrainian ministers. Hopefully, she is not mine because it was publicly available. So I can prompt the model to fetch the text and see if it can cope with this. Just takes a little bit of time because it like generates one token at a time. and I'm using HTTP request to prompt the model. So in this case, we can see that basically the result is pretty good. Yes, just here, yeah, it's wrong. Here it's wrong, but we can see that like it's a difficult task really for the model. Moreover, it was just trained on the synthetic data, but like we see, almost all words are accurately predicted. And what I want to emphasize is this particular section here, that it actually was able to decouple all these words and like put this statement, all these statements correctly in the reading order. So we have like date, we have name from right to from left to right. Another example, I can show maybe a table extraction example. So here, this is just some random snapshot from internet, but here we have a table, and here we have a prompt I used for fine-tuning and benchmarking. And here we can just prompt the model to fetch the table from this image. So what I want to emphasize, that model can actually detect that we have like row span here, we have row span here, we have a column span here, and basically model actually detected this, and we have like resources with 2 rows and so on, right? And all these data points, they actually wrapped into the correct text. I have one more example. So here we have just a page, again, randomly found in the internet. So very likely model wasn't fine-tuned or trained on this initially. So this is article, a newspaper article about education. And so what I wanted to show, that's basically ability to classify this document. And here I have my original prompt, and my original prompt, I did not have a like education category among my within the training data set. However, so it predicted as a literature. Yeah, that's what I wanted to do. Oh, sorry. But if I add education and then prompt it again, I get education, because information about education prevails in this article. I can even fetch this complete text, but if you are okay to wait, because the generation of the single token and the long sequence takes time. Okay. Yeah, and basically I'm done with the presentation. Thank you for your attention, and yeah, I'm ready to answer to your questions.
Okay, thank you, Andrei.
I can start. Thank you, Andrei, for your presentation. It's interesting, and the reviewer give you high mark. But let's deep into some details. So you proposed like different types of synthetically generated data, and you mentioned these classes like hand, print, and scan. So what is the difference?
This is not the classes. This is just like style. I used HTML templates and CSS styles, so this is just my way to like scan.
So what's the difference between those 3?
Print, just regular print, regular document without any degradation. Okay. Scan, I implied like degradation techniques similar to the scan artifacts.
Can you give us some example?
Sure.
Of the such image?
Sure. I can actually, I have another tab open here. So this is This is the document. This is the data set. And here you see like I have this style column, so I can open any scan document. Now this is a very long one, but you see like it has this.
Can you zoom in, please?
Zoom in. Oh. I don't know how I can zoom in on Hugging Face. Maybe like this. So
okay, and all those different changes on the document. So you have some some references on how to do this, or it's all it's your own ideas how to apply those different filters.
It's it's available publicly on Hugging Face. I have a repository. I have all prompts, all styles, all templates.
Yeah, I mean, so this typical task, I assume that it's a quite typical task, how to make this pseudo scan document, right?
It was basically my idea, just like use HTML templates and styles, CSS styles.
Yeah, and
this.
Was it your idea also a set of those different distractions, or you find out somewhere on literature? So what kind of filter you applied here?
Here you see like we have this sinusoidal mapping, so it's like simulates the curve that basically.
Yeah, my question here is it your own approach to apply such filters?
I think I just was searching and looking what can be done. So yeah, it's basically my ideas. I did not find on the literature. It just basically make it closer to the scanned artifact. That's basically.
But okay, and then you have this whole spectrum of different sets of filters, starting with the pure like printed without any diffusion, and then where to stop on this spectrum? I mean, how many filters?
It vary in some range. Yeah, have some range, like how drastic this impact of this filter should be. So it's just randomly selected with every new sample. It just like applies this type of imperfection or another type of imperfection.
Do you have any like worst sample of the scan documents?
The worst one. Second.
Because my question is that all samples you showed us are quite good, let's say, for the OCR task. Even handwriting font is quite well scanned, well processed.
No, I won't be able to find it, just the worst one. It's probably more or less the same across all these. We can make them worse, but I wanted just some positive results. I didn't want like just make it completely impossible for the model to.
It's a bit, biased towards positive results.
I agree. That's why
That's why I have a question regarding the. Can you jump back to your presentation and the slide where you have those diagram of the fine-tuned model?
Okay. Sure. Just since I am switching the sharing from window to window, so here we actually got the result of this prompt. Tuning the graph, this one?
No. The results.
Results. Okay.
And then the next was the diagram.
Okay.
Yes, this one. So all those high numbers, almost like 100%, it looks like overfit. So what's your test and train data? So train data, we see it, and what about test data?
Test data was just like 20% of the same data set. So we have like 80-20 split in this case. So the overfit, I would call it adaptation, high level of adaptation. Because model, again, I did not train all layers. I use LoRa, so I injected layers, certain layers, so model still remembers what it should remember.
Okay, my suggestion would be to put all those find from the internet, the sources you showed us during the demo session into the test.
Definitely, yeah, that's.
Have you did it?
No, I did not. This is in the future work. This is mentioned in the future work, and this is definitely not enough.
Yeah, because it's really interesting work, but the results are a bit, you know, like in the sandbox. Like it's like very good prepared data set, and we expect the good, as you mentioned, bias towards positive results.
Mm-hmm. No, we can say that not all open source models were able to cope with this data set. We found that P multimodal and IA vision.
Because what do you think? Because of the Ukrainian language?
Probably because of the just like how they were trained. They probably were not designed to deal with the text, right? They maybe were trained just on images, just like scene images, or they were not very carefully trained on the text. However, Qwen was specifically trained on the text itself. So it actually can deal with like small pixels, with small characters. So it goes much better. That's just a matter of training.
Okay, thank you.
Thank you very much for your presentation. I want first to add that you trained on synthetic data. And that's the reason why these scores are so high. And I understand that we never have a lot of real data, but when we train such kind of model, it would be good practice to arrange some small maybe data set for test and test that for real data. But example that you shown us was wonderful. Anyway, I have one more question. You have a LoRa adapter. How you choose rank of this adapter?
So this was the part of the experiment to just try different ranks and pick which one.
Evaluate.
Yeah.
Oh, that's cool. And you mentioned handwriting data. How you and you generate some artificial handwriting data for you to train?
No, this is just like fonts, different fonts, handwrite like fonts.
Fonts, not real handwriting.
Not real, yeah.
Yes.
Real.
One more question. Your title, document understanding. What do you mean understanding? Because if I understood right, you tested your model like recognition using all recognition metrics, so optical character.
Correctness rate.
Yeah.
Character correctness.
So it is why understanding?
Because it's not only OCR, it's also classification. So document can like just detect the class of the what the information is about.
Thank you.
Thank you, Andriy. And just a small suggestion. We would be very interested in your work in understanding the students' handwriting when they write their final or midterms, because we couldn't understand something. Data set, yes.
Okay. For 10 years.
Thank you, Andriy. I also have a couple of maybe minor questions. What was the resolution of the image you used for training?
It was a high resolution. But like images itself, it was a high resolution just to mimic the structure of just like a regular page, A4 page size. So it was like up to like height was 1,200 pixels, I guess, and the width was around 800, I guess. but we did not train like our data set. As I explained, we actually applied the data set inflation process. So which actually means that we train, we at the same time, we have like a complete document, and we pass the complete document with one prompt, and then we pass the just separate regions of the document with exactly the same prompt, just fetch text or fetch table, but we just feed those cropped regions instead of a complete document. That's why we have both. So we have two prompting strategies.
Mm-hmm. And maybe a bit philosophical question. So I remember that this OCR capabilities, so I guess maybe one or couple of years ago, only GPT could do that, and the other language vision language models were not able to do OCR. And maybe do you have an intuition how does this how does this capability emerge into large language model?
Just like a regular evolution, I guess. First, you can just like write, then you can see and write, and so on. So this, I think, those connectors will just my personal opinion. I think those multi-modal connectors, they will be expanding wider with multiple modalities combined together. Since like basically we probably reached a certain limit of LLM itself. However, just combining modalities and getting the results from the shared embedding space is like probably interesting and promising direction.
Thank you for presentation. Yeah, maybe just getting back to the question with data set and to the question with too high results. I suspect that it is really the issue, maybe not even your training data, but mostly that you test on the same like synthetic data. And that is why like the data distributions are really same, and they might not represent the real one, like the real ground truth labels that you might have. But just getting closer to the question, as I understand, you have used multilingual models. So I'm curious whether have you tried to compare these metrics that you get on your Ukrainian data set, for example, with metrics on some English OCR data sets. I believe there are like some data sets for benchmarking. So you can compare like correlation, whether like models that perform better on your synthetic data set, do they perform better also on English data set? Have you tried something like that?
Unfortunately, scope of this research did not allow me to experiment like that. But that's an interesting suggestion, right? Could be explored in the future work. I just want to comment one point that like specifically, okay, like OCR data set wasn't completely synthetic. Data set was semi-synthetic because we used real text from Wikipedia. So this text wasn't generated. It was the real text from Wikipedia, just incorporated in documents. We used tables. The table structure was actually, it's a real data set, public table 1 million data set. It's researchers from Microsoft who created this data set. So when we generated documents, we were actually sampling from that data set of the tables. And as we can see on this chart, we see that table extraction is also high. So it's still high. It's like randomly sampled from the real data set and with tables, with just HTML tables, and it's still improved. That's just wanted to mention those 2 points.
But I think just in order to be like to be more sure that your data distribution is not shifted, it makes sense just to take, for example, like real, for example, English OCR data set, which is not generated, like generate the same one, but for English using your methodology, and then compare how the results differs or the same. So in such a way, you can be more confident that your data distribution reflects like the real one and is not shifted like some way.
Yeah, that's a good suggestion, as I said. However, there are no like document data for data sets for documents for visual document understanding. There are data sets for captions, like the fairly small sentences, but you don't have like a real dense page with many tables, everything else. That's like not available, unfortunately, even in English, at least publicly.
Okay, thank you, Andy. Move on to the next work in this session. Will be presented by Roman Kovальчук, who was supervised by Mariana Romaneshin and Petro Ivanyuk. And his master thesis is entitled Multilingual Natural Language Processing with Large Language Models as a Case Study of Grammatical Error Correction for 11 Languages.
Can you hear me well? Okay, great. Just a second, and let's start. So the subject of my thesis is multilingual natural language processing with large language models, a case study of grammatical error correction for 11 languages. I'm being advised by Mariana Romaneshin and Petro Ivanyuk. And speaking of, I'm highly grateful to them for that invaluable support. And we also express gratitude to AppSuku for providing computer resources and OpenAI API access. And we express our gratitude to the volunteers, students, and lecturers of the National Technical University Kharkiv Polytechnic Institute who joined and promoted our annotation project. We also thank Alexander Skorzansky and other reviewers of our study for their invaluable input to this work. We are going to start from the motivations, and we are going to discuss a background relevant to this work, related work itself, problem setting, approach, which is aimed at addressing the research gap we found, such as new GC datasets we called OmniGC, dataset quality evaluation, methods for evaluation of those new datasets, and LLM fine-tuning experiments involving that new data. Then we are going to overview the outcomes, limitations, and future work of the study. Speaking of motivation, multilinguality is an increasingly popular topic not only in grammatical error correction field, but also in natural language processing. It is apparent as newer OpenAI's models such as GPT-4o, 4.1, and reasoning models are more frequently marketed as being more capable, not only in their bare power, but in English, but also in their ability to process low and mid-resource languages. Also, there has been research papers published from Grammarly on multilingual GC, and GC competitions been conducted on multilingual GC study in the last 2 years, such as MultiGC 2025 and MultiGED 2023 by the University of Gothenburg. However, there is an apparent problem. Although of those new advancements, there is apparent lack of studies, and we can clearly see that English is fairly under-researched, with the most work concentrating on English GC, and multilingual GC is being less covered, which makes our work more timeliness and valuable. Speaking of background, we think that it is important to differentiate between minimal and fluency GEC edits. And in the domain of GEC, we differentiate between minimal edits and fluency edits. The minimal edits are responsible for correcting only the necessary grammar error corrections while keeping the original wording and structure. And in fluency edits, we are allowed to rephrase to produce a more smooth native-like sentences as long as the meaning stays the same. So in minimal edits, we reward pinpoint accuracy, and in fluency edits, we reward more idiomacy, publication-ready text, and readability. Another important notion is a differentiation between silver and golden GEC datasets. So GEC corpora are typically released in two quality tiers. Golden dataset is a dataset when every sentence and edit is written and double-checked by expert annotators, guaranteeing near error-free labels, but making this dataset scarce, time-consuming, and expensive to produce. Whereas silver datasets are generated automatically, and only a small sample of it is spot edited by humans, enabling orders of magnitude data at a minimal cost. Yet some annotation noise remain. So speaking of golden data yields top quality corrections, whilst silver delivers the volume. Speaking about related work, we split this section in 3 tracks: English monolingual GEC, multilingual GEC, and multilingual LLMs. English GEC is the most research area in related work. English GEC methods like high diversity and ranking, which achieved sorter results on English GEC, is highly adaptable to, can be adapted to other languages, whilst other methods such as Vector, for example, a ranking model for English GEC, is specifically designed to work with English, making this transition problematic. Multilingual GEC is highly related topic to area to our study. However, it is under-researched area with very few published papers. Nonetheless, approaches like synthetic data generation mentioned in the UNLP 2023 is highly related to our work because it is easily adaptable not only for other languages other than Ukrainian. Multilingual LLMs we chose for the study are AI Expanse and Gemma 12b. Speaking of open source models, they both are highly capable not only in multilingual setting, but also in GEC itself. And speaking of proprietary models, we have utilized GPT-4 Mini and O1 Preview for synthetic data generation. As I mentioned, for pre-trained LLMs we chose for the study, AI Expanse covers 23 languages, including Ukrainian. And speaking of Gemma 3, the authors do not explicitly state which languages are supported. However, they state that there is a support of 35 out-of-box languages and pre-trained support for over 140. AI Expanse is more compact than IA 101, and it also performed, which also performed well in a GC setting. And Gemma 3 is more capable than Gemma 2, which yielded top results in multilingual GC 2025. And it is also a highly capable model in GEC and multilingual task as well. Speaking of datasets, notably there is only one golden high quality multilingual GEC dataset released as part of multilingual GEC 2025 competition, and is fairly limited in terms of number of examples. This dataset consists from 12 different corpus, different in annotators, subject, objective, and so it is highly diverse and not uniform dataset. Although it is best we have, and it is yet intricate to avoid this non-uniformity in datasets in multilingual GEC. It covers 12 languages, and 11 of them are our target languages in this study. Also, there is highly popular English GEC datasets such as CLang 8, Cohen and 2014, and BAA 2019. They are high quality and high quantity, but as mentioned, they cover English only. Speaking about GEC competition, as I mentioned, there is Multi-GEC 2025 as the most recent multilingual GEC competition, and previous competition, Multi-GED 2023. They differ in number of languages. Nonetheless, the data included in Multi-GEC 2025 covers the data previously seen in Multi-GED 2023. multi-GD 2023 does not methods does not involve LLMs, and methods are generally outdated, whilst multi-GC 2025 yielded relatively low scores, and we judge that by not beating SOTA scores from monolingual competitions such as UNLP 2023 for Ukrainian. And speaking of UNLP 2023 for Ukrainian, as I mentioned, competition covers only Ukrainian, but the method are easily adaptable to multilingual setting. Speaking of metrics, there is a difference between a heuristic and LLM. There is a tendency to using LLM-based metrics such as Primendi, and edit distance is a number of edits to manage reference text. Character error rate is a normalized version of edit distance. F.5 weights precision twice more than recall, which is important in GC. Errand is a method to extract precision and recall. GLAO serves the same purpose, although it is n-gram based. It is also being used in multi-GC 2025, and we also utilized that metric to compare our results. Speaking about identified gaps, we identified the following gaps, such as data collection gap, data composition, and low solution performance. As we mentioned, high-quality GC data is scarce. Multilingual data is not uniform. There is lack of data quality versus data quantity ablation studies, lack of cross-language ablation studies, and as I mentioned, results of multi-GC 2025 do not beat a SOTA for individual languages. We are going to, we have addressed the gaps, such as data collection gap by publishing new GC datasets, which were published on Hugging Face. We have collected uniform multilingual data and automatically collected silver GC annotations, and we assess data quality with manual and automatic evaluation methods. For data composition, we suggest to conduct ablation studies. However, we opted out of such work to time limitations to future work. However, it is important to study impact on per language basis and study impact of data quality versus quantity on a per dataset basis. For low solution performance, we have utilized techniques from English GC, applied fine-tuning to open source large language models of different sizes, collected preference data for Ukrainian as a case study for DPO fine-tuning. Superficially, we adopted methods and techniques that worked well in English GC. Speaking of OmniGAG, it consists from three corpuses: a Wiki-edits multi-GC, a Reddit multi-GC, and UberText GC. They are different in their number of examples, and they're different in a manner of annotation. For example, Wiki-edits multi-GC is annotated by Wikipedia contributors, meaning humans. However, we found that on our human evaluation study that it yielded the lowest results, and we will discuss that later why. Reddit multi-GC and UberText GC are GPT generated and sourcing from Reddit and UberText social corpora respectively. We expect Reddit to more closely resemble a natural distribution of how humans typically type, therefore being more useful in inference. Speaking of synthetic data generation, the method used for UberText and Reddit, it consists from three parts. The first one is prompt generation, where we want to generate two pairs of prompt. The first one is aggregation prompt and multiple correction generation prompt. What is idea here is that this method is closely is very related to the SOTA English GC method, high diversity in ranking. What we want to do is we want to generate three possible corrections per each sample. And then with another shot of GPT model, we want to aggregate those three possible corrections into one, therefore yielding more complete and holistic prediction. And we do so by utilizing O1 preview and translation models under prompt generation. We use the Golden GC dataset, and we select examples per each language. And with O1 preview, we select those examples and generate few short prompts for 11 downstream languages. We use those prompts to generate a data set of multiple possible corrections per each sample of unlabeled data. And then we use translated prompt with DeepL and another GPT for mini shot in callout number 3 correction aggregation to aggregate three possible corrections into one, yielding a labeled data in the end. Speaking about quality evaluation, we perform automated and human evaluation to measure the dataset quality on a subset of 1,500 samples per corpus in Ukrainian, because we were more eloquent in it. And yes, speaking about methods, automated evaluation is scalable, cheap, and uniform. However, it is rather limited. We used as reference predictions from relevant GEC systems such as Правописник, Explorator, and language tool in Ukrainian as possible targets for our predictions. And for human evaluation, it is accurate, representative, but low scale, expensive, and requires language expertise. And as a reference, we use annotator assigned grades. Speaking about the results of automated quality evaluation, we used multi-reference, as I mentioned, with Правописник, Explorator, and language tool as 3 possible target corrections versus 1 hour correction yielded by the synthetic data generation method. And the interesting thing here is that Reddit multi-GSE yielded the highest F.5 score, whilst having the lowest GLAO score. And for Wikidata's multi-GSE, it is vice versa. We suppose the difference being is that in Wikidata there is quite like very few edits in a Wikipedia page. Therefore, the n-gram resemblance is pretty high, so the GLAO score is higher. And the picture is different for Reddit corpora because it more frequently requires complete rewrites. Speaking of human evaluation, we involved 15 annotators, native speakers of Ukrainian with a major in linguistics, on 3 corporas, each having 1,500 data samples, and 100 samples were double annotated for calibration. Speaking of quality grades, there is 5. For a grade of 1, we count such corrections in which new errors were introduced or the meaning has changed. We don't want to have that in our final system. For a grade 2, we count such corrections as having major errors, but unchanged in meaning. For a grade of 3, we mean significant improvement over the original text, but minor errors remained. For 4, we mean grammatically correct correction, like minimal grade correction in GC datasets. And for 5 grade, we mean correct and fluent corrections involving idiomacity, syntax corrections like fluency grade, Here's the result for our human evaluation. As we can see that more than 70% of data generated synthetically are scored as 4 minimal grade or 5 fluency grade. And as we can see from this picture, Wikidata's multi-GEC yielded the lowest scores. Nonetheless, we found in our fine-tuning experiments that a model using that data yielded the highest GLAO score across all languages, and we will see that a bit later. Speaking about error analysis, we identified that overcorrection is a common error present in all datasets. Lower grades in Reddit multi-GC are largely due to the presence of a non-ethical or inappropriate content, which we tried to filter with Omni moderation model from OpenAI. However, it is automated manual method, and it can be improved in future work. Speaking about lower grades in UberText GEC, it is largely due to the presence of additional and essential text such as promotional content, and grades 1 and 2 were most relevant in Wikidata's multi-GEC, which is due to extra information present in Wikipedia edits. Speaking of examples, here's an example of fluency grade corrections made by our annotators. As we can see, the corrected text is grammatically correct, and the syntax both synthetically and grammatically. However, an interesting example is more than original example, and as sound example of that 1 grade, we have the following. So if you read the first sentence, we have that the Rasmus Band performed Stefania's song on Eurovision. presenting Finland. But in original sentence, we have that the Rasmus only singing Stefania song, but they are not thereby presenting Finland in that tone. So the meaning has changed, and therefore we assigned a score of 1 because the correction has different meanings than the original text and being less useful in GEC. Speaking about GEC system flow, we use fine-tune LLM to correct user messages and use a text-to-correction parallel dataset we have collected OmniGEC and train a large language model to correct user messages more precisely. Speaking about LLM fine-tuning setup, we used zero-shot prompting, with AYA model to develop instruction templates and instruction tune AYA expands 8B and geometry 12B with those templates in 3 incremental setup, involving first multi-GEC data, then multi-GEC plus Wiki-edits data, and the last multi-GEC plus Wiki-edits plus Reddit data. And we measure how additional language-aligned corpora translate into performance in multilingual GEC with GLAO score. Speaking of results, there is results in GLAO mean, minimal, and mean fluency. Mean means an average score across all languages. As we can see for AYA model, it far surpassed model from multi-GEC 25, Llama 3 8B, in more than nearly 9 GLAO score points. For minimal track, for fluency track, they did not submit submission. And we can see that GEMMA model at first yielded lower scores than AYA model. However, with addition of Wiki data, it yielded even better scores than AYA model trained on multi-GEC plus Wiki plus Reddit. Yes, and we suppose the difference is being that GEMMA model is underfitted because we only trained it in one epoch due to resource and time limitations. Nonetheless, that experiment still proves that adding more target-aligned and language-aligned data improves LLM's performance in multilingual GEC and surpasses the latest paragraph-based state-of-the-art model from a multi-GEC 2025 with 56 GLAO score points. Speaking about deliverables, we introduced new GEC dataset openly published on Hugging Face called OmniGEC. We collected new preference data and published that as part of our OmniGEC collection on Hugging Face. The code repository is openly available for future contributions and updates. OmniGEC data. Speaking about models and paper, we have published 4 models: OmniGEC minimal and fluency for 8B option based on AYA expands, and OmniGEC minimal and fluency 12B option based on geometry, also on Hugging Face collection. The code repository for instruction templates and LoRa fine-tuning is openly available for reproducibility on OmniGEC models, and a supplementary research paper has been accepted to UNLP 2025. Conclusions, we have addressed the following gaps: data collection challenges with publishing new GEC datasets and low solution performance by utilizing techniques from English GEC. Gaps to be addressed, conduction of ablation studies, which we opted out to future work due to time limitations. Speaking about limitations, OmniGEC covers only 11 languages, leaving aside the vast linguistic diversity. Human annotations were only collected for Ukrainian, limiting assessment and DPO fine-tuning for other languages. And we used proprietary models such as GPT and reasoning models from OpenAI for synthetic data generation, which impacts the reproducibility. And due to time and resource limitations, GEMMA was only tuned for one epoch, as I mentioned, for multi-GEC plus Wiki-edits plus Reddit scenario. Speaking of future work, we want to conduct a human evaluation for new datasets in more target languages, DPO fine-tune model for, again, more target languages, compare DPO with KTO method, explore full fine-tuning, and explore newer base models, LLMs, GEC methods, and approaches. Thank you for attention. If you want, I can finish here, or I can continue with answering reviewers' comments as part of my presentation. Sure.
There are no questions from examination committee. So, okay, I will start. I'm curious, how does the model size impact the performance? For example, you have been studying relatively small large language models, right? So there are much larger models. Maybe you can give us some context. How do they perform on other languages when maybe more data is available? And what do you think about using large models for Ukrainian?
Okay, so the first interesting thing involving a model selection and performance on languages, we have identified that our OmniGC corpora benefits the models which were not pre-trained on target languages, such as, for example, Latvian for IA23. Estonian, I think Estonian as well. So as we can see, it benefits the system the most. OmniGC results are yielding the highest performance gain, and only a slight gain with moderate gain on languages which were present in the pre-trained process of pre-training. However, authors of IA mentioned that model size is very important in terms of scaling the model to new languages, and that also was factor of choosing 8B plus models. However, the authors of the most recent survey paper in English GC mentioned that models of higher than 12B are more dependent on quality of data rather than a model size. Therefore, we might concentrate on improving the data quality, but as we can see, there is generally there is two dependencies. So first one is data quality, and the second one is model size, yielding from the system being multilingual. So in English, you see it is more dependent on the quality of data for higher model parameter models.
Thank you very much for your presentation. If I understand correctly, you have one model for all these 11 languages, right?
Yes, with two options. Four options.
Okay,
So
let's start with one model, and I think your approach is very scalable. So you can, if you have time, money, and inspiration, you can extend it for a lot of languages, right?
Yes, we built our system so
it's,
it is adaptable to other
scalable approach. And what do you think? You mix here different languages. I mean, Cyrillic based or Slavonic language and English based. It's for good or not that you mix different languages, or maybe your model would work better if you collect similar languages somehow, or maybe if you train your model on all these languages like foundation model, and then just fine tune a few epochs for each separate languages. What would be the best?
Thank you for the question. And speaking of, we have identified that interlinked more languages does not yield worse results. For example, we have started with including only fine-tuning only on Ukrainian data, and then we included all of 11 languages present in multi-GC competition. And what we faced that increasing Ukrainian GLOW score in like 10 or 15 scores, so it is rather beneficial to include other languages, as we find out. And the authors of Letty's team, who has presented Llama 3 model in multi-GC 25, also state that including more languages yielded higher scores when using LLMs for GEC. However, a more thorough study is indeed needed with ablation studies, as we mentioned, to identify the cross-lingual dependencies.
Thank you. Thank you very much.
Yeah, sure. The first question was why were more sophisticated fine-tuning methods not explored? And we suppose that first of all, most experiments run on a single A140 gigabytes GPU, and full fine-tuning triples the GPU hours and costs. So we landed on using only LoRa fine-tuning instead of full fine-tuning. Although the authors of the most recent survey paper mentioned that full fine-tuning increased their results in 5 score points, which is not a marginal improvement. And we would definitely consider that in future work. And yeah, it still supported our hypothesis that adding more target-related data enhances LLM performance in multilingual GC, even with our lightweight setup. Then the question, did you observe any overcorrection patterns when aggregating 3 GPT-4o mini corrections? Have you considered an ablation study? We expected some degree of overcorrection in the final edits, as on the aggregation step, we merged 3 possible edits from GPT-4o mini into one, increasing the edit distance in the final correction. We consider that the benefit of output being more complete would far outweigh the overcorrection bias, and our human evaluation study suggests that 70% plus of examples are scored as minimal grade or fluency grade. And due to time and cost limitations, we opted out of such ablation study. And yeah, that's it.
Okay, thank you, Roman. We should have had 40 minutes break, but since we finished 12 minutes earlier, we will have 52 minutes break. And we will start at 4 p.m.